Start చేయండి.
A very good morning to distinguished guests, esteemed faculty members and dear participants. Welcome to the 5th day of ACT-sponsored ATAL FDP on Artificial Intelligence-based Energy Storage System integrated with renewable and sustainable energy sources for electric vehicles, organized by Department of Electrical and Electronics Engineering, NRI Institute of Technology, Agirpalli. Today, our chief guest is Dr. D Sreenivasa Rao sir from NIT Warangal. Coming to the brief biodata of Dr. D Sreenivasa Rao sir, he was born in Andhra Pradesh, India. He received his B.Tech degree from Bapatla Engineering College in 2006. He received the M.Tech and PhD degrees in Electrical and Electronics Engineering from Indian Institute of Technology, Roorkee in 2008 and 2014 respectively. He is currently working as an associate professor with National Institute of Technology, Warangal. His research interests include power quality, multi-level inverters, modulation techniques for multi-level inverters, development of new converter topologies, electric vehicles and adjustable speed drives. He has published more than 20 research papers in various journals and presented more than 10 research papers in various international conferences. He has supervised 3 PhD scholars and guided around 50 graduate and undergraduate student projects. He has delivered more than 200 lectures in various conferences, workshops and short-term courses. Now I request Dr. D Sreenivasa Rao sir, so please start the session.
తీసుకుంటారు. ఇదో
in the other applications like microgrid, UPS, or the like DSTATCOM, all these applications. So we use some different types of batteries. So how these batteries will be charged, so that we will study in today's this entire 2 sessions. Right. So we'll start with the basics of battery charges for electric vehicles. Next we'll start with what kind of batteries are used or what kind of energy storage systems that are possible, so that we will discuss. Right. So first we'll start with this. So battery charges for electric vehicles. Right. So the first and foremost thing is that, so when you're studying this electric vehicle battery charges, the primary thing that we use is the power electronics. Right. Here all mentioned study the power electronics at your various categories, maybe third year, final year you might have studied this, right? So here, these are the different kind of applications in electric vehicles, so where the power electronic circuits are used. Okay. So everything in any electric vehicle, so almost all the control circuits are derived from the power electronics only. Okay. So that may be some may be a lowest voltage level of 2 volts, 3 volts, 5 volts range. So whereas some other will be in the range of 400, 800 volts range. So you can see all the applications like the airbag deployment. Right. So and this one lighting, front lighting, heads-up display, and engine control. Right. So all these things that we require power electronics in some form. Right. The power rating may be very small in some applications. So whereas in some applications we require the highest amount of power. So this is the vehicle architecture. So where exactly we use this. Or where exactly we can place the different types of batteries. Right? So let us assume that, so this one is the, what is this? The high voltage battery. Right. So this is high voltage battery here and here. So we have some low voltage battery. Right. So imagine this one is an electric vehicle. Right? So here you know what the voltage rating of this high voltage battery? How much it is? What is voltage rating? Typical voltage rating of a battery that are used in the electric vehicle. It is normally 400 or 800 ohm. So depending on the architecture they are used. Right? Some vehicles use the 400 volts battery. Some vehicles use the 800 volts battery. For example, some luxury cars they normally prefer the 800 volt battery. In case of vehicles like Tata Nexon or some mid-range vehicles, they prefer the 400 volts battery. Whereas applications for two-wheelers, they normally prefer 48 volts battery or 52 volts battery. In case of two-wheelers like Ola, scooters are there like Ola, Acer, or those normally use the 48 or 52 kilowatt or the voltage batteries. Understood? So here we have this low voltage battery. So this is common in all vehicles, whether it is a diesel or the petrol or electric vehicle. This is common. So it is typically 12 volts or 48 volts. So this is known as the auxiliary battery. Okay. So this one is known as the auxiliary battery. So that is common in all vehicles. That is just to start the ignite the vehicle. We require some battery. We have spark plug will be there. So using the spark plug, so we need to ignite the in case of gasoline engines like petrol and the air combustion engine, that we need to ignite that. For that we require high voltage. Right. So we normally use a second order system that consists of inductor, capacitor, and some DC source. Right. The DC source is from the battery. Right. So where we create some overdamped response. From the overdamped response, that will produce some high voltage. Appear the spark plugs, the spark plugs it will ignite. Right. So from that ignition, the fire will be generated. The fire is used to fire up the air and the petrol mixture. So that is how a spark plug will be work in case of a petrol engine. Right. So whereas for other applications like lighting, right? So this 12 volts or 48 volts will be used. Early days we use 12 volt batteries. Nowadays all the luxury cars or electric vehicles they are using for the 48 volts. Right. So based on that, so there are two types of architectures will be there. This is 12 volts or 48 volt battery architecture. So whereas this one is 400 volts or 800 volts architecture. Right. So there are certain advantages are there. So when we go for 800 volts, so that we will discuss at point of our class. Right. So we have this main battery will be there, right? So to charge this main battery, or if you observe that this one, this thick line is the bus, DC bus, high voltage DC bus. So typically this voltage is around 400 or 800 volts, right? So if you observe that, so we have this one, right? What is this? Inverter, right? So what is the use of this inverter? Which will convert the DC to AC, right? So here we have the electric machine or the electric motor will be there. So which is typically a three-phase machine. So what kind of machines we use in these electric vehicles? So we normally prefer the induction motor or the permanent magnet synchronous machine. So induction motor or the permanent magnet synchronous machine. So nowadays mostly we are using the PMSM motors only because of the reduced weight. So we prefer this three-phase permanent magnet synchronous machine, or sometimes we use the brushless DC machines, or sometimes we use the interior permanent magnet synchronous machines. A lot of options are there for this. A lot of options will be there for this. So we prefer the induction motor or the permanent magnet synchronous machine. So mostly we use the permanent magnet synchronous machine for this case, right? So here, so this one, so what is this one? So this crankshaft, right? So that means it is changing the motion, right? It is changing the rotational motion into the linear motion, right? So here, depending on the vehicle, so this motor is connected on the front wheels, rear wheels of both sides, right? So let us assume this is front, right? So this motor power is connected to the front wheel. So that is known as the front wheel drive. If it is connected on the rear wheels, the same arrangement is on the rear side. So that is known as the rear wheel drive. Understood? So engine power or the motor power which is connected to the front wheels or rear wheels depending on the front wheel drive or the rear wheel drive. So nowadays we are seeing that the 4x4 vehicles are there, right? So that means, so here the engine power, so that is connected to the both front wheels and rear wheels. Right? Sometimes they use the same motor or the same crankshaft. Sometimes they use the different motors. Right? So let us assume that one motor here attached to the front wheels, another motor which is attached to the rear wheels. Right? So the motor capacity will be same in some cases the motor capacity will be different. So let us assume this is 300 kilowatt motor sometimes. So maybe at the rear wheels they use the 200 kilowatt of same motor. That all depends on the design. Right? So those are known as the 4x4 vehicles. Right? Understood? So this one will convert this DC into the rectified AC. Right? So 3-phase AC, the 3-phase AC is connected to the motor. Right? So from this the motor will be rotated and this one will convert this into the linear motion. Understood? So if we observe that the power flow is bidirectional here. This tool indicates that the power flow is bidirectional. So why it is bidirectional? So why it is bidirectional? You might have studied the regeneration, right? So when you are decelerating or when you are climbing down a hill, so what happens? So whatever the stored energy or the kinetic energy stored in the wheels, right? So how the regeneration works? So when it is rotating, it consists of some kinetic energy. So that kinetic energy, so that we can absorb, right? So that we can absorb and we can convert this into a electrical energy, right? So from this electrical energy, so we have this AC, right? Now this motor will operate as a generator, and from this AC we can generate DC here, and by using this DC we can charge this battery. Understood? Whatever the kinetic energy of this wheels, so that we can transform into charge the battery. Right? So here from this wheels to here, so from the crank to the motor, this motor will act as a generator, and this one acts as a AC to DC conversion. Right. So this is a bidirectional converter. So we normally say it's inverter, but the actual thing it is bidirectional. Right. If we give DC input, it will convert AC. Similarly, if we give AC input, it will convert into DC. Understood? So from this DC, right, so we can charge this high voltage battery. Understood? So this is how a regeneration will work. And another thing is that, so we need to capture the regeneration very fast. Right? We know that, right? What is the formula for kinetic energy? With the velocity is V. It is of mv square, right? So that is the energy stored in the wheels. If the speed is reduced by, or velocity is reduced by of, how much energy will that? Only 25%, right? It is of mv square, right? So let us assume that V, if it is reduced by of, the energy is reduced to 25% only, right? So that means we need to capture the energy as quickly as possible, right? So when automatically when you are before applying the actual brake, we need to capture the entire energy, right? Understood? So this is how a drivetrain works. This entire thing is known as the drivetrain of the EV, right? So now the point is that, so we need to charge this high voltage battery. We need to charge this high voltage battery. There are two options are there. So one is the on-board charging and the other one is off-board charging, right? So the name itself says that in case of on-board charging, so what happens is that the charge is placed inside the vehicle, right? The charge is placed inside the vehicle. So whereas off-board charging, the charge is placed outside the vehicle. Understood? So here, so this arrangement, so this one and this one, so this is the on-board chargers. So each vehicle is equipped with some on-board chargers. Right? It may be single phase or three-phase input. It takes single phase of three-phase input. Right. So let us consider this one. Right. So here this one is a single phase inlet for the onboard charger. Right. So first we have this AC here input. This AC is converted to DC here. Right. So AC is converted to DC, and here we have another DC-DC converter that will match with the battery voltage. Right. So that will match with the battery voltage. So from this case, the power flow will be from this grid, right? So to this DC, and from this DC-DC converter to this. Understood? So we have required two-stage conversions. One first thing is that so we convert this AC to DC, and another thing is that after that we need to use another DC-DC converter. That another DC-DC converter is to match the battery voltage and the converter voltages, right? So you observe that there are two lines are there, right? So here you have only one line here, and here two lines are there. So here the meaning is that see that there are two lines here, right? What it means? It's an isolation, right? So how isolation is provided in electric circuits? How an isolation is provided? By using a transformer, right? So transformer gives you the best isolation, right? So why it is required isolation? If something is wrong on the one side, so that should not be carried forward to the other side. For example, if there is no isolation here, if something is wrong here on the AC side, so that will be damage the high voltage battery. Right. Similarly, something wrong on the DC side, so that may also damage the protective equipment on the AC side. So to prevent that, so you usually require some isolation. So that isolation is provided by using a transformer. Right. So there is a difference between the transformer that we use in power transformer, and there is another one is a high frequency transformer. Right. So this transformer inside this is an high frequency transformer. Right. So what is the frequency that operates normal transformer? It is 50 or 60 Hz, right? Normal transformer will operate at 50 Hz or the 60 Hz. So whereas high frequency transformer that will be operated at 50,000 Hz or 100,000 Hz, right? Like 100 kHz or 50 kHz or even higher than that. So you know the advantage. So when you go for high frequency, the size will be reduced. Right. So if you compare some imagine if it is 50 Hz transformer of the same rating, the both size. So right? Some we are same rating, same kVA rating of transformer we are comparing. One is the low frequency transformer and another one is the high frequency transformer. So imagine if it is a 50 Hz transformer, so this much size, the screen size. So whereas 50 kHz transformer, this is just this much only. Right? Just this much only, the same rating, same voltage and current ratings, the transformer is this much small. So that means the size will be drastically reduced. The size of the transformer is drastically reduced. That means almost 95% of the size will be reduced when we are using a high frequency transformer. Okay. Understood? So this is single phase. So here we convert this AC to DC. We have this DC-DC converter here. So you might have doubt, right? So you already obtained DC here, right? You already obtained DC here. So why this stage is required? So why this stage is required? So from this AC to DC conversion, you already obtained the DC, right? So why this is required? So there are two reasons for this. The first one is that so there are if you want to charge some battery, right? There are certain algorithms will be there. So one common used algorithm is the constant current charging, constant voltage charging. Right? So in case of constant current charging, so what we will do is that so we will keep the current constant. Alright? We will keep the current constant. So we will vary the voltage. So in case of constant voltage charging will keep the battery voltage constant and will vary the current, right? So therefore, this voltage will not be constant, right? So this voltage is not constant. So here we are getting a fixed DC here. So from this point we are getting a fixed DC. Sometimes, for example, 400 volts battery is there. So this voltage will be vary from somewhere between 360 volts to 440 volts, right? So you cannot charge with a fixed voltage. So depending on the algorithm or depending on the charge method, so whether it is a constant current control or the constant voltage control, so this DC-DC converter works. For example, it requires 410 volts, right? So from here you are getting 400 volts. So this will convert this 400 to 410 volts. Understood? It requires 360 volts only. So it is reduced the voltage to 360. Understood? Right? So there are some charging methodologies out there. So one is the constant current charging, constant voltage charging. In all you can also observe in mobiles also. So have you ever noticed that from 0 to 80%, if you take some time, from 80% onwards, the charging time will be drastically reduced. From 80 to 90%, it will take more time. From 90 to 100%, it will take even more time, right? Because what we are doing is that we are cutting down the current, or we are cutting down the voltage, right? Understood? The same applies here. The charging algorithm is not unique, it will be varying. So that's why you require some additional converter. Right? So this is the in-phase inlet. This is same thing, but this is 3-phase inlet. Right? So if the charging is done from a 3-phase supply, you require some 3-phase supply here, so AC to DC conversion, and you have DC-DC converter here, so that will charge this high voltage battery. Understood? So these are known as on-board charging. So on-board charging typically requires AC power supply. On-board chargers require AC power supply in single phase or 3-phase. Right? So in case of single phase, it will charge at low power, it is around 1 to 2 kilowatt range. So whereas it will be around 10 to 15 kilowatt range. Right? So whereas other one, right? So this is DC charging, or in other words, it is known as charging at a charging station. Charging your vehicle at a charging station. So for that, so here this grid is there in the charging station. So from that, so we have this ultra fast charger setup is there. But what exactly inside that I will show you in the next slides. So from this, we have the DC-DC converter, and we are directly charging this battery. Understood? So we have charging can be classified into onboard charging and off-board charging. So that is one thing. And another thing is the AC charging and the DC charging. Right. So this is AC charging, right? And whereas this one DC charging. So directly we are charging the battery. Right. So this one, so typically less time. So here the battery or the charger rating will be in the range of 350 kilowatt or 500 kilowatt, even 100 kilowatt range like this. Whereas AC charging will be 2 kilowatt or 10 kilowatt, that's range. Right. So to charge this battery here, it typically requires 20 minutes, half an hour or 45 minutes. So whereas here, to charge from the single phase supply, it will take at least 20 hours to fully charge the battery. Whereas with this, it will take 10 hours to fully charge the battery. Whereas this one, so by using this, it will typically require 25 to 45 minutes to fully charge the battery. Understood? So depending on the power levels, so we have this onboard charging and the off-board charging. Right? So next thing is that, so here how to charge this low voltage battery. In case of diesel or petrol engines, we have the dynamo will be there. So the dynamo when the motor is rotating, right? So we have the dynamo will be some small internal generator will be there. So the generator will charge or discharge this battery, right? So whereas here that option is not available in case of EV. So So here this battery will be charged by using this main battery. This auxiliary battery is charged from the main battery itself. So therefore you have this high voltage DC bus here. So from this we have another DC converter. So let us assume this 400 volts. So this voltage may be 12 volts or 48 volts. Right. So we have another DC converter here. So from this DC converter, so we can charge this high voltage battery. So low voltage battery. Understood? So this battery is essential for all active passive safety systems, or even this battery will be completely engaged even when the engine is completely off. Okay. So here from this, so we have some low power loads like lighting inside the vehicle, mobile chargers, or some interior lighting, or some active and passive safety equipment. So that will be run so based on this low voltage power supply. Right. So there is this high voltage or this high power loads like air conditions. So inside this vehicle air condition will be there. Right? So from this high voltage here, so air condition draws more amount of power. So therefore we have this AC to DC converter here. So from this we have this one is the air condition motor. Right? So from this draws from high voltage or high power loads like air conditions. Understood? So this is the complete power architecture of some electric vehicle. So a lot of power electronic circuits will be involved. Some DC-DC converters are there, AC to DC conversion and DC to AC conversion. So all these things will be there. Yeah. Understood? So next thing is that the point is that how the batteries are rated. Right? How the batteries will be rated. Right? So we observe that this battery rating is depends on your applications. Right? So let us assume that your smartphone will be there. So we observe that the battery capacity will be 4000 or 5000 milliampere hour. Right? So 4000 or 5000 milliampere hour. So what it means? 4000 or 5000 milliampere hour means in 1 hour it will draw or it can dissipate a current of 5000 milliampere. That means 5 amperes of current it will dissipate. Right? In 1 hour if you continuously run the and if it is drawing 5 amperes of current, it can withstand for 1 hour. If you are increasing the current, right? If it will, for example, we are drawing 10 amperes current from your mobile, so that means it can withstand only for half an hour, like this, right? So whereas here, in case of electric vehicles, right? So here the rating is in the range of kilowatt hour. Right? You understood? In case of your smartphone mobiles, so that is in the range of, that is designated as milliampere hour. Right? So whereas here, so it is designated as kilowatt hour. The difference is simple. In case of electric vehicle or some vehicle board, so the voltage is not fixed here. The voltage is having some range. The voltage range may be in the range of 400, for example 400 volts, it will be in the range of 360 to 440 volts. Right? So whereas in your smartphone mobile or smartphone battery, the voltage is fixed only. Right? Voltage is 12 volts or 5 volts, so that's fixed voltage, and it will always emit the power at a fixed voltage. Right? So that's why it is denoted as milliampere hour. So whereas this one, so this 60 kilowatt hour, what it means is that we are continuously run this machine or this motor for 1 hour, right? So it can deliver a power of 60 kilowatt. It can deliver a power of 60 kilowatt. Understood? Right? So to charge this 60 kilowatt, right? So we can choose, let us assume that we have choose, so let us assume that we have choose a charger, so which is operating 1.4 kilowatt. We choose a charger which is 1.4 kilowatt, right? So how much time it will take here?
400 minutes.
How much it is? 40 hours, right? Correct? It will take 40 hours to fully charge the battery if you are charging at power supply or it is drawing 1.4 kilowatt. Right. Same thing, it is slightly increased to 7.2 kilowatt. So what happens here? How much time it is required? It is somewhere between 8 to 9 hours, right? So here it is increased to 50 kilowatt charger, right? So you require only 75 minutes. If it is 120, you require 30 minutes. And if 37, if you observe it 350, you only require 10 minutes to fully charge the battery. Theoretically. Practically, the charging will be depends on a lot of factors like temperature, voltage, charging algorithm, right? Theoretically, it requires only 10 minutes to fully charge the 60 kilowatt hour battery. Understood? So one will be observed that so one is slow charging and another one is the medium fast charging and another one is the fast charging and ultra fast charging. Right? So this is slow charging, right? And this is also slow charging. So this one is fast charging, whereas this one is known as the ultra fast charger. Correct? Understood? So based on that, so we categorize into 3 levels. So one is the level 1 charging, right? And this is level 2 charging. So whereas this one is level 3 charging. Right? So usually this level 1 and the level 2 are AC type chargers. Right? AC type chargers, in other words, it is known on-board charging. So we need to input 3-phase supply here. So here we need to input 3-phase supply at your parking lot and your garage. Right? So whereas this one is DC charging, right? So when you are going for this 50 kilowatt or 350 kilowatt, it is not AC. So we have to rely on the DC, and the DC is directly connected to the battery terminals. Understood? Okay. So here, so this is known as level 3 charging. So this is known as level 3 charging. Right. In other words, it is known as charging your vehicle at the charging stations. Right. So this kind of facility is not available at your home. Right. So we need to go for the charging station if you want some high power charging. Understood? So based on this level 1 and level 2 and level 3, so we have some powers of categories here. So let us assume that it is AC charging here. So we have level 1, level 2 and 3, right? And here, this one, so there are charging standards are there, right? So we have some charging standards are there. So like this one is SAE. So this SAE stands for the Society of Automobile Engineers, and this IEC stands for International Electrotechnical Commission, International Electrotechnical Commission. And whereas this CHART-EMO, so this one is CHART-EMO standards, this is China and the Japan, some standards are there, and this is Tesla standards, right? So this SAE standards, so this is used in America, North America, like in USA and Canada. So they use this SAE standards, Society of Automobile Engineers standards. So this IEC standard, so International Electrotechnical Commission. So this European standard, so this CHART-EMO, right? So it is originated in the Japan and China, right? So nowadays every worldwide we are using this CHART-EMO standard. So this Tesla is the proprietary one, only uses the Tesla electric vehicles, right? So now the point is that so all are earlier we have some divergence is there. So nowadays all are interoperable, right? So all these chargers are interoperable. Meaning is that, right? For example, when you are buying some EV, right? If you give some specifications, right? So that means your EV will require some charging standards. Maybe it will rely on this SAE standard or this IEC standards or this CHART-EMO, right? So that means you need to go a particular charging station, so where they follow these standards, right? So that is the case earlier. So nowadays we can, all the charging stations will follow this SAE standard, IEC standards and the CHART-EMO standards, right? So that means the interoperability is there, right? You don't need to worry about your vehicle is supporting this charging station or not, right? So that is known as interoperability. Right. So in case of India, so we are following this IEC standards. In India, we are following this IEC standard. Almost all for everything we rely on the for all standards like Euro standards or PS5 standard, PS6 standards. Right? We rely on the European Union. So this is IEC standard is for the European Union. Right. So the point is that so we have AC charging, right? So this is the charging standards, right? So in case of AC charging, this is for level 1, level 2, and this is level 3, right? So whereas here, so in case of DC, right? So we have this level 1, 2, and 3, right? Similarly for DC charging, so in case of SAE, so we have this 36, 1996, and this is for IEC standards in case of DC, right? So this is also same here. So whereas this chart demo, so here in case of chart demo, this is only DC charging, right? So this chart demo is it is some consortium of different automobiles like Ford, Toyota, and this Volkswagen and all. So they form some consortium. So based on the consortium, they came with some standards. So this is known as the Chardano standards, right? So maybe in future, so they will want to follow these standards, right? So they are also projecting standard for the ship propulsions, right? So that is known as megawatt chargers. That is for ship or some aeroplanes, or maybe in future they are expecting some ships with electric, with batteries, right? So that means that requires some megawatts range, right? So 2 megawatt charger, 5 megawatt chargers, they are proposing for the ship propulsion units, right? That is known as the megawatt charging systems. So this Tesla one is, as we discussed, is a proprietary one, right? So now earlier it is 135. So now I think they are moving to 350 kilowatt charger after the introduction of the Cybertruck, right? Understood? So what we observe that the charging is AC charging and DC charging. AC charging is charging at your home, whether it is single phase is available and 3 phase is available. Single phase it requires 20 to 30 hours to fully charge your battery. In case of 3 phase, it will take 10 to 12 hours, right? So whereas DC charging, so that is charging at the charging stations that typically require less than 1 hour, right? So here, based on that, we divide into level 1, level 2, and level 3 based on the power range of the how much time that fully charge the battery, right? So next thing we observe that we learned that every charger must follow certain protocols or charging standards. So we have SAC standards are there, IEC standards are there, charging of Tesla chargers are there. Similarly for China, there are some GB standard is there. So that is for China. Right? Understood? So next we have different charger manufacturers are there in the worldwide. So these are common. So this one is ABB, right? This is TTM. So this is some copper-based company. So this is ABTech. So these are based structure. So this is the voltage rating. So we observe that output voltage is not fixed, right? So you can see that the output voltage is not a fixed one. Even though the battery voltage is fixed, but the output voltage is not fixed, right? As we discussed that sometimes we need to keep the, or sometimes we need to vary the voltage, right? So we need to vary the voltage of the charger, right? So therefore this voltage is varied here, and here this is the current and this is the efficiencies. So next thing is that so every charger so must specify some standards, right? So as we discussed, so these are the standards. So when you are designing some new charger in the market, you are introducing some new charger, right? So that must be specified with these compliances, right? So for example, this J1772. So these are the standards. So they will specify the limits, right? So how much voltage you need to give, right? What kind of harmonics are generating, right? And another thing, what kind of how much noise it is generating. So every charger must be passed with these things. Right? If you ever observe that on the back side of your electronics, there is something written like FCC CE is written, right? Have you ever seen that, right? Like CC, CE. So that is certification, right? So when you are introducing some new electronic thing, so that must be certified, right? So they will check thoroughly, so whether they have some standards, so whether they are following the standards or not, so they will check, right? So for example, Bluetooth, Wi-Fi, there are some particular standards will be there. And it should not, for example, in case of mobile network, it should not be all the environment. So they will check continuously, check the health hazards and all, right? Similarly, this is SAC standards, and these are the standards that is used for the IEEE. So this is for the grid interconnection, smart grid, right? And this charging network management, and this DC fast charging. So they will specify the guidelines, right? So they will specify the guidelines. Similarly for IEC also, so they will specify the guidelines, right? Similarly for India also, so we have some guidelines, so that guidelines we are supposed to follow. So next important thing is that, so what kind of connectors we use, right? So what kind of connectors we use for charging, right? So this is known as the main pins, right? So this is known as main pins. So we have this connector is there. So this is SAE J1772, right? So we observe that this J1772, so that is comes from here. Okay. Right? So this is SAC standard. Right? So we see here, right? So what you observe that this one? So this is AC charging, right? So this L1 indicates the phase here, right? So this LT indicates the neutral. So this is phase connection, and this neutral connection. So this is protected earth, right? So this point is earth. And we have two signals are there, CS and CP. CS and CP are for the communication, right? CS is the control signal and CP is the control pilot. So these are for the communication. So why it is required? So you will continue monitor, right? What kind of, how much temperature is there, so how much charge is there, or whether it is properly connected or not, right? So when it is fully charged, right? So to read those algorithms, we require some communication, right? So for the communication, so we have the CS and CP pins are there, right? So this is the single phase charger. So this is phase and the neutral, and this middle one is the earth. Right? Same thing here. So this is same thing, but this is different from this is three phase, right? So this is A phase, B phase, C phase, and this is neutral, and this is protected earth, and this CPP are for the communication, right? So these are important for the communication. So that will decide only the charging speed. For example, temperature is increasing, what we will do? So we cut down the power, right? So for example, it is already charging is already reached 90%. So we need to slow down the charging, right? To increase the health of the battery, so we need to slow down the charging, right? From 90% onwards, so from for example 95, we need to slowly cut down the power, right? So further, so this communication is required. Understood? So this is single phase charging and this is three phase charging. Similarly, we have, so these are known as the combo connectors, right? So these are known as the combo connectors. So these two are for the DC, this positive and the negative. Understood? So this is positive and negative. Same here, single phase. This is combo connectors, right? So we have only one plug. So from that plug we can feed both AC and the DC, not simultaneously, right? So when you are connecting to the AC, so obviously DC will be blocked, right? Similarly, this is three phase, AC and DC, right? So this is three phase, AC and DC, right? So this is the one we are in India we are using, right? So we can charge single phase. This system is for charging single phase, three phase, and as well as DC. Okay. So that's why it is known as CCS. CCS is combined charging system. CCS means combined charging system. That's why we usually call a CCS system or CCS charger, combined charging system. Right. So we are mixing all single phase, three phase, and DC. Right. So that's why we are getting only one plug. Right. So that plug is used for single phase, three phase, or the DC charger. Right. So usually it is following the Renewable standards. It is based on the IEC standard. So this is same thing, but it is only for DC. Right. So this is only for DC, and this one is CHAdeMO standard. Right. So this is CHAdeMO standard. So nowadays this is very popular. This CHAdeMO standard, which is very popular, especially for 350 kilowatt range chargers. So similarly, as we discussed, CHAdeMO is only DC charging, not AC. Right? It is always DC. There is no AC here. So these are for this one. This is for to start here, right? And this one is the CAN bus, so control area network. These are for the communication, right? So this is the chart standards. So this is used in the China, right? GB is not Great Britain. So this is some Chinese standards, right? So all Chinese standards all we will start with GB only, right? So GB by T, so that is Chinese one, right? So this is Chinese standards. Right? Similarly, this one is the test bus proprietary AC charger. So proprietary DC charging. Right? Similarly, we have some pins are there. You don't know what kind of pins it is there. Understood? So these are the different main pins so that are available, right? So these are the different main pins so that are available, and we follow this one. So CCS means combined charging system. So you can charge single phase, three phase, and as well as DC. Right? The point is that when you are charging single phase, so remaining will be blocked. Right? Similarly, when you are charging DC, and the AC is blocked here. Right? So this is exactly what is there. On the other side, let's even play. Right? So this is contact 1 here. Right? So you can support that 80 amperes up to 600 volts here. Right? And this is contact 2 here. And these two are for the DC. Right? So as we discussed, so this one, right? So this is for the control status, monitor, so read switch, with proximity detection. So detection is connection to the status to the vehicle is properly connected or not, so that will be identified with that pin. Similarly, this one, so this one is a control pilot switch or control pilot connection. So we measure the AC levels, right? And in case of PC, so whether the communication protocols are followed or not, so that will be checked from these pins. Understood? So this is for the DC, right? So this is for DC. So here also the ratings are given. In case of AC charging, so level 1 is around 1.92 kilowatt for level 1 charging. So it is 3 phase or single phase it is 2.2 AC charging. So whereas this one, in case of DC it is 48 kilowatt, or level 2 is 400 kilowatts. So this one, so this is protective air. So this charge is grounded. Right? So that is directly connected to the vehicle. Right? So this is directly connected to the vehicle charger. Right? Understood? Do you have any questions? Any questions? So next we move to the how the battery charge will be applied. Right? So now a battery charger is required. Right? See, as we discussed, so this is AC side, right? So this is AC side, and the battery is connected on the other side, right? So here, first thing is that, so we have input AC is there. So immediately after that, we have some filter network will be there, right? Some EMI filters will be there, so that will suppress the electromagnetic interference. EMI filters that will suppress the electromagnetic interference. So this is common in almost all electronic circuits, right? Whether it is a battery charger or anything, right? It is common. Right? When you are open the, for example, any power supply, you can open it, right? Or whether it is anything like whether it is LED driver or anything. Right? So first thing immediately found is that so this choke filters, so that suppress the high voltages or some rapid voltages or something, right? Or such voltages. So to suppress that, we require some filter, right? So next thing is that so we need to convert this AC to DC. So next step is that so we need to convert this AC into DC, right? So how AC is converted? We are using a rectifier circuit, right? So rectifiers are, you might know that there are two types of rectifiers will be there. One is controlled rectifiers and uncontrolled rectifiers. So controlled rectifiers is based on the diodes. Uncontrolled is based on the diodes, and whereas controlled rectifiers based on the resistor of the LCRs. So we can control the output voltage by changing the current magnitude, right? But the point is that so that kind of rectifiers we are not use, right? So that kind of rectifiers we are not use. So instead of that, so we have used this power factor correction rectifiers. So this PFC stands for power factor correction rectifiers, right? So this PFC stands for power factor correction rectifiers. So meaning is that, right? So meaning is that
markup teaches it.
So we see that this is starting point here, right? What is this? A direct bridge rectifier, right? So on the DC side, we have some inductor is there and capacitor is there. Inductor will smoothen the current waveform, right? This capacitor will smoothen the voltage waveform, right? So this one acts, this LC will act as some filter. This LC will act some filter, and we expect that this output voltage will be fixed one or it is ripple free. There will be no ripples on this waveform, right? So we observe that so this one, right? This line is there, right? So this is the current that drawn from this rectifier. So that means if you measure the current here, if you measure the source current here, the source current is in this shape, right? So this kind of shape we are observed on the source side, right? Understood? Right. That is the point. For example, this AC power supplies or this LEDs, right, or this projector. If you see the or if you observe the current waveform, so this kind of current it will drop, right? And if you observe that, you might know the harmonics and all, right? So that waveform is not a sinusoidal waveform, right? And it is drawing some peak current here. So here current is absent. So here all the current is absent, and we have sudden rise in the current, right? So we have sudden rise in the current. If this kind of rise in the current, so that will also distort the voltage waveform, right? So this kind of rise in the current, so that also distort this voltage waveform, right? So it's not only spoiling the current, so that may also spoil the voltage shape, right? So therefore, what we can done is that, so we have some other converters, right? So we have some other converters. The converters will make this current sinusoidal, right? So that currents make this sinusoidal, and at the same time, so this current and this 2 will be in phase. Understood? So that is what known as the power factor correction. Right? Understood? So power factor correction means it is drawing more reactive power. What is power factor? It is the sinusoidal current and voltage supply, the cosine of the angle difference between the voltage waveform and the current waveform, right? Okay, so power factor 0.6, 0.8 leading or lagging, so that means it is drawing some reactive power. But the reactive power is not required, right? So only you require the, or you are interested in the real power, right? So to make reactive power 0, so when it will be 0, cos phi, right? So cos 0 is 1. So that means the angle difference between sine wave or the current wave and the voltage wave, so that's supposed to be both are in phase. Right? If this voltage and this current both are in phase, so under this case we will get unity power factor, right? And in that case you will get, or in other words, it will only transfer the real power. So we will not use any reactive power here. Understood? So when you are only drawing the real power, so that means the burden of the circuit will be reduced. Right? Understood? You know that, right? Because the current consists of both active and the reactive terms, the total current will be increased, right? So that will increase the power bills. To reduce that, so we have to make sure that we draw only the real power. Right? So we have circuits are there, so that circuits will draw. It will make this source current sinusoidal and at the same time in phase with the voltage waveform. Right? So this is what it is known as the AC to DC PFC power factor correction, right? So meaning is that, so whatever the current here, right? So that is sinusoidal and it is in phase with this voltage waveform. Essentially this converter is operated at unity power factor. Alright? So after this, so we have some DC will be there, right? So next we have this isolated DC-DC converters, right? Isolated DC-DC converter, and we have some filter on the DC side. So we normally connect some LC filter on the DC side, and from this filter, so we will ultimately feed to the battery. Right? So to control all these things, so we normally require some microcontroller. Right? So we normally require some microcontroller or some digital signal processors, something like that. Alright? Understood? We require some digital signal processor, FPGA boards, or microcontroller, and all these things are controlled by this. Right? So this AC to DC, then DC to DC, and also on the battery side voltage. Understood? So this is the basic architecture of a battery charger. Right? If we go deep into this, the actual power circuit will be something like this. Right? So we have this AC supply is there, some filter is there. Right? So this entire thing is known as the power factor correction AC to DC circuit. Right? And here, so we get DC. So this one is the DC-DC converter. Right? And here we have the high frequency transformer. Here we have high frequency transformer. On the other side, this one is the filter here, and here this is the battery, so this is ultimately connected. Okay? Understood? Similarly, same thing here, right? So the difference here is this is unidirectional charger, as we discussed. So the charger may be unidirectional or the bidirectional. So when we have to use bidirectional charger, so when we can use the bidirectional charger. So we have some applications like vehicle to vehicle, vehicle to grid, grid to vehicle, or vehicle to load. So there are four things are there. So one is the vehicle to grid to vehicle, vehicle to grid, vehicle to load, and vehicle to vehicle. Right. So grid to vehicle, so it is obviously common thing, right? So from the grid power, so that is feeding to the vehicle. So that is more common. So whereas grid to vehicle, vehicle to the grid, so that means if they, for example, if the EV is equipped with some solar, so on the top sometimes they can equip with some solar or some outside, right? So that will charge, right? That will charge the battery. If the battery is excess, so that means that excess power, so we can feed it to the grid. That excess power, we can feed it to the grid if the vehicle is equipped with some solar panels, right? That is known as the vehicle to grid. Similarly, we have vehicle to load is there. So vehicle to load means, in all EVs, vehicle with some, that comes with some vehicle to load function. So we can connect somewhere around 3.6 kilowatt load we can connect, right? So that load we can connect to charge some your two-wheelers, like electric cycle, we can charge, or some two-wheelers we can charge, right? Or else we can run some equipments which rely on the DC supply, right? So which is known as the vehicle to load. So whereas vehicle to vehicle charging, right? Vehicle to vehicle charging, so that is two things, right? So here one vehicle from one vehicle battery to the other vehicle battery we can charge. So let us assume that this is one battery placed here and another battery placed here. So we can transfer from power from one battery to the other battery, right? So we can transfer power from one battery to the other battery, which is known as vehicle to vehicle charging. Understood? This is usually, for example, when the vehicle starts somewhere, right? So one vehicle will come, and from the vehicle inside that some batteries will be there. From that battery, you will charge your battery, right? Here the chargers will be two types. One is the unidirectional charger and the bidirectional charger. So unidirectional charger is sufficient, but the design of bidirectional charger is simple when compared to unidirectional. Therefore, almost all electric vehicles use this kind of charger only. Okay. So they use this kind of charger inside there. So they have found this charger, and this is the high frequency charging. These are the different power converters are used, and so next we will see how a charging infrastructure, in other words, how a charging stations will look like, right? How a charging stations will look like, right? So let us assume that this is one charging station, right? So this is one charging station. So here the input for the charging station is some DC, some AC input, right? So we have this medium voltage AC input, right? So it will be voltage will be around some 3.3 kV to 11 kV, right? So this voltage will be some 3.3 kV to 11 kV range, right? And after that we have this low frequency transformer will be there for isolation, right? And we have three-phase AC is there, right? Three-phase AC is there, and from this AC, and the point is that almost on every charging stations they equip with some solar panels, like some other solar panels or some other alternative energy sources they equip, right? So mostly with solar. If it is a DD area, they may be integrated with some wind energy system or some wind turbines, right? If it is a DD area or if it is near to the seabed, they may use some wind energy sources. So most of the times they use the solar panels, right? So here, so AC supply is there. So here on the on-site we have some solar generation is there, right? So the point is that, so why we are using solar panels here? The first thing is that at the charging station, so a lot of space will be there, right? Requires one space to park the vehicles and all, right? So the rooftop or usually the roof will be equipped with some solar panels, right? We have a lot of empty space will be there, right? So we can easily equip that. The first thing is that is first thing. Another thing is that so we can reduce the ownership cost. We can reduce the ownership cost. So another assume that in case of India, we are not charging the based on the demand based pricing. Right? In case of some other countries like Europe and US, what they normally do is that they will charge based on the demand. Right? So when the demand to the power supply is very high, so at that time they will charge more. For example, evening time and peak time, right? So unit price may be, for example, here the unit price may be 7 rupees or 8 rupees an hour per day. And during the peak time they will charge you 10 rupees, 11 rupees likewise. Right? So they will suddenly increase the price, so when the demand increases. Or when there is no demand is there, so they will reduce the price. Right? Okay. So here, in case of when it is very high, demand is very high, so in that case, we have on-site PV generation. So from this PV generation, so we can charge this vehicles. Okay. The point is that so whenever you have a PV, so you must have a energy storage system. So when you have a PV, you must have some energy storage system. Okay. So why it is required? If you have PV, you must have some energy storage, right? So why it is required? Why it is required? If you have PV, so energy storage is required, right? So PV is not intermittent power, right? It is highly varying. If it is a cloudy day or during night times, you cannot generate PV. Right? You cannot generate PV power. So what we normally do is that whatever the PV power generated during the daytime, we will store it and so depending on the cost, when it is peak demand time, right? So when it is peak demand time, in that case, they will store in the or they will be feed to the grid, right? When the demand is less, right? So in that case, they will store the PV power into the batteries, right? Or else they will charge the vehicles here. Understood? So this is just an optimization problem, right? So PV is generating power, right? We have some loads are there. You can feed this PV power to the grid. For example, there is no load is connected here, no vehicle is charging here, right? So whatever the PV generated power, so that will be used to charge this battery or energy storage system. Even though it is also filled, in that case what we will do? So we transfer this power to the grid. Understood? Right? So that you will get some profit. And another thing is that grid is charging more price. It is a peak time. Right? It is a peak time, right? So instead of taking from the grid, so what we can do is that so we will use this energy storage system to charge this vehicle. Understood? So lot of options will be there. So depending on so which one gives you the profit, so that we can operate. Right? So that's why we have almost all charging stations will equipped with some PV. Right? So that PV power we can use it to charge the energy storage system, or you can use it to charge the vehicles, or we can use it to feed to the grid and we can get some profit. Right. So that's why almost all nowadays almost all LP charging stations are operating with almost zero or negative bills. Right. So instead of paying for the power supply, so they are actually getting for the they are getting some money. Right. So just they want to maintain the charging stations, the structure. Right. So next we go to the technical details here. So PV will generate the DC power, right? The PV is DC power, but we have the AC here. So to integrate that, so we require some DC-DC converter here. So inside this we have MPPT algorithms are there, right? You know MPPT? So that is maximum power transfer characteristics. So PV is non-linear between voltage and current, right? Some point we need to identify so where you can deliver the maximum power, right? So this will operate with MPPT, and we have this inverter will be there. So this PV DC, so which is converted to AC, which is connected to this grid. Understood? Similarly, this one also, energy storage system also there, right? So this is where is DC. So we have DC-DC converter for charging, and we have inverter. So this is DC-DC inversion, and it is connected to here. Understood? Similarly here, you require DC supply here, AC to DC conversion, and again DC-DC conversion, and this is here. Is clear? Clear? Every time, so we have this AC bus is there, right? So we can cut down this one, or we can reduce some converters, right? So what we done is that, right? So we change it to DC here, right? So what we done is that, right? Immediately after this AC, right? So here immediately after this AC, we change this to DC, right? So we have converted this into DC here. So this is DC here. So AC to DC conversion, and this is DC supply. Okay? You understood the difference? So here all this PV energy storage system and this charge is connected to the AC supply here. So whereas it is connected to the DC supply. Right? So now we can reduce the power converter. So this PV is DC, right? So therefore one converter is enough, right? So this battery, so only one converter is enough. So this is already DC, we already converted this. So one converter is enough, right? The point is that, so by using different instead of using multiple AC to DC conversions, so we directly convert this AC to DC at the beginning itself, right? AC to DC at the beginning itself. Alright, understood? So this one is known as the AC microgrid. Alright, so whereas this one is known as the DC microgrid. Right, so this entire thing, so we can operate as a microgrid. One is AC microgrid and another one is DC microgrid. In other words, one is AC architecture and another one is DC architecture. Right. For example, we have some wind turbines are there. Wind and wind power generation is there. Wind power is what kind of source? AC or DC? Wind power is AC or DC? Wind power is AC or DC? It is AC, right? Wind turbine. From wind turbine, it is connected to some induction generator, right? So induction generator is three-phase AC, or it is connected to some induction generator or some synchronous machine, right? So that it will generate the AC. So the point is that in case of here, if your wind turbine is also there, we want to integrate wind turbine. So AC is already there, right? So you just need another converter. We can directly integrate here, right? So whereas here wind turbine is there, so here the point is that here DC is there, so we need to convert AC to DC. Correct? Understood? So depend on what it is available, so we need to change. Right? So in case of PV, so this is the best option. Right? If it is wind turbines are there, so instead of the so in case of PV, so this is the best option. It will minimize the power electronics. Want to connect some wind turbines and all, so this AC microgrid is the best option, right? Understood? So that will minimize the power electronic circuits, right? And some operational difficulties are there. For example, protection AC is simple. So in case of AC, protection like low voltages, short circuits, under voltages, protection is simple. In case of AC, we have natural zero, right? So this AC waveform naturally will become zero, so the protection is simple. So whereas in case of DC, there is no natural zero. The DC waveform is continuously positive or continuously negative. There is no natural zero, right? So that case of protection is slightly difficult in case of DC. Right? So that things we need to check. Right? So this is how a simple electric vehicle charging stations look like, right? It may be a AC architecture or it may be a DC architecture. Okay? So AC architecture is preferred when your wind turbines are there or something is there. In case of DC, if you have some DC or if you have some PVs are there, so we can prefer this DC architecture. Okay? And another thing is that so every time, so when you have a battery, every time when you have battery on EV, you must require some DC-DC converter. Right? So we cannot directly charge from here. So every time we require some DC-DC converter, whether it is an energy storage system or it is a battery. Both are ideal similar only. You also have charging battery, you also have charging battery. Both are similar only. Right? So you need battery and you need some extra DC-DC converter every time. So this design approach so completely eliminates the transformer, right? So this completely eliminates the transformer. So here this isolation or inside this one. So inside this DC-DC converter we have some isolation. So as we discussed, inside this we have some high frequency transformer is there, right? So rest of the things are same. So rest of the things are same. So that means now we can we have some options are there. So generally in case we are connected to 11 kV or something, we normally connect some converter to the we don't have converters of 11 kV. Like so therefore in between you require some transformer. So now we can eliminate the transformer. Right? So now we can eliminate the transformer if you want. So next we will discuss about the wireless power charging, right? You know that, right? Wireless power charging and the reverse wireless power charging. So nowadays all the mobiles are equipped with these two features. So one is the wireless charging and the reverse wireless charging, right? You know that, right? Wireless charging means you connect some mounting pad will be there, right? So from the mounting pad it flows from that it will be charged. So what is reverse wireless charging? What is reverse wireless charging of your phone?
From phone to the other device.
Other accessories. For example, on the back side of your phone you have this, right? So if you want you can charge some your AirPods or something, right? If you place it here you can charge that, right? So that is known as the reverse wireless charging, right? So nowadays it is common. So wireless charging is the contact free, right? There is no physical contact between the source side and the physical side. So all can be done through the magnetic induction, right? So this is also known as the inductive charging. So one is the wireless charging and the wireless charging. So there are other names is the conductive charging and the inductive charging. So far we discussed the conductive charging. So that means through the physical wires. So there is induction charging. This is through the induction, right? Magnetic induction principle, right? So remember that. So this both circuits are identical, right? So battery charging circuit, battery conductive or inductive chargers, so both are identical, right? So only difference is that here. So only difference is here. So this is same, circuit is same, right? So whether it is a conductive charging or wireless charging or wireless charging, the circuit is same. So only change occurs is that, so this point, right? If it is both primary, this is change here. Both primary and secondaries are inside there, right? Inside the some circuit. So that is conductive charging. This secondary is separated, right? This secondary if it consists only primary, secondary is on the receiving side. So that is known as wireless charging. In case of wireless charging, after this cone it will be there, right? So rest of the circuit will be on the secondary side, right? On the receiving end side. Understood? This circuit is on the receiving end side. So we have this high frequency AC will be there. So this high frequency AC, so by using this magnetic induction principle, so we convert this high frequency AC here. So this AC, this direct bridge is converted to DC here. So now this DC is fed to the battery. Right. Understood? So there are three principles or three common applications based on this. So one is the wireless charging, wireless charging, and the induction cooking. You know that, right? Induction cooktop?
Yes, sir.
Right? The application is same. So from here, the circuit is same. Right? In case of wireless charging, so this circuit is also only the pins are available at this point. In case of wireless charging, so this entire circuit is on the receiving side. Right? This entire circuit is on the receiving end side. In case of induction PT, you know that induction PT, right? So these terminals are there, right? So these terminals, this high frequency AC terminals, which is connected to the workpiece, right? It is connected to the workpiece. From the principle of workpiece, eddy currents will be induced on the workpiece, and the eddy currents that is equal to the I square of losses. That losses will induce the heat. Understood? There are three things, these three circuits are same, right? Up to primary side, so that is common. If the secondary side is also included, so that is while charging. If the secondary circuit is on the other side or the other side of the equipment, right? And the other equipment, so that is wireless charging. The secondary terminals are connected to a workpiece, right? So that is known as induction heating. Understood? All are same. In case of induction heating, so when you connect this one, right? So when it is the point where you are short circuited, right? Right. So that short circuited to the workpiece. So from the workpiece, so the power it will be induced. Eddy currents will be generated. So that eddy currents will generate the heat, and the metal piece will be heated. The principle is same. That is the wireless, wired, or the induction heating. Okay. So when it comes to the details, so this circuit, as we discussed, this is same. Right. So we have AC to DC conversion, and this is DC to AC. So here this is high frequency AC here. So here this is 50 Hz. So where this one is in the range of 100 kHz or 50 kHz or 200 kHz range. Right. So it's 100 kHz, 50 or 200 kHz range. Right. So from this, so this is fixed one. So whereas this one is moving here. Right. So this is attached here. So there is a difference between this. So this is known as the coupler circuit. So from this coupler circuit, so when you are placing this one, so there will be EMF is induced on this coil. So from here it is conversion, and it is ultimately to the battery. Understood? Right? The both primary and secondary are completely apart. So that is wireless charge. Right? If both primary and secondary are completely in one circuit or one box, so that is wireless charging. The secondary terminals are connected to the workpiece, so that is induction cooking. Right? Same thing here. So nowadays we can observe that wireless track will be there. Some green tracks or wireless track will be there. The road pavement is completely filled with the inside there some circuits will be there. So as and when you are moving on that way with your vehicle, right? So it will charge, right? It will charge. The same thing here. So we have this track will be there. So this is the track. So when you place a vehicle here, so from this vehicle we have this pickup coil will be there. Right? From this pickup coil when you place here, so due to the mutual inductance, the EMF is induced on the secondary coils. So from this, So we have this AC to DC conversion from DC from here. So we have AC to DC, DC to AC, and it is ultimately fed to the battery. Right. So this is how a wireless charging is used. Right. So normally wireless charging we have some restrictions on that. So we cannot transfer more amount of power due to these losses and due to the alignments. The first and proper thing is proper alignment is required. Right? If the alignment is not proper on the secondary side, the coefficient of coupling, right? So it is expected that the coefficient of coupling is as high as possible. So if the alignment is different, it will reduce the coefficient of coupling, right? In that case, it will reduce the secondary side EMF. So therefore, it will also reduce the secondary side power. Right. We have other wireless transfers also there, like microwaves we can use, right? And electrostatic coupling we can also use, and this EMF electromagnetic fields we can use. So we have, if we are using some microwaves, right, for the power transfer, the disadvantage we have some radiation will be there, right? And we can also use some electrostatic fields. So with electrostatic fields we can deliver some low amount of power only. Right. So compared to these three, so this one is the best option. So with this we can send the power, right? So nowadays research is going on to send power in the kilowatts range. So we can send some power in 250, 350 or 500 kilowatt range power we can send by using this. Right. So whereas in case of mobile chargers also, so we can send power 100 watt or something like that. In case of reverse wireless charging, maybe we can send 50 to 25 watt power in the reverse direction. So these are the different manufacturers or the different labs that are working on this. Right? So these are the YTG, Toshiba, Bosch, and Nova here. Right? This ETH, Toshiba, and this. These are the different working on that. And this is the power that is transferred, right? So we have 250 kilowatt or we have even 120 kilowatt. So this is the amount of power that is transferred and that is under the research. Okay? So we have as of now, so we can transfer up to 500 kilowatt of power. So for this, as you know that, right, we require the pickup coil of the receiving end device. Right? So we have a lot of options are there. So one is the circular pad. Right. So this is circular pad. So if you, in case of this, mostly common this one is the charging pads, circular pad. Even in mobile phones also, on the back of the battery. Right. The first thing, as and when you open the back cover, you will normally find this. Immediately after that, we have NFC coil will be there, or NFC chip will be there. So NFC chip is for the payments, and immediately after that, you will find this kind of coil, right? And after that, you will find the battery, right? So after opening the back cover, you will find the NFC chip. And after that we have this magnetic coil, and after that you find the battery. So this circular pad, right? So we place the receiving will be like this, and this is for the rectangular pad, and this is PE pad. So it may be two materials. One is this is aluminium, and the coils are made with the ferrite. So ferrite is used for the high frequency applications, right? Nanocrystalline ferrite materials. Powder iron is used for the high frequency coils, whereas for the silicon steel or these are the core material that is used in the low frequency transformers. So we have this one bipolar pads, right? And this extra pad is for the pickup compensation. For example, if there is misalignments are there, it is not properly placed, right? It will reduce the power. To avoid that misalignments, we have two pads will be there. So this is also the same thing for the this extra yellow one is for the misalignments, right? And this one is for 3 phase, right? This A phase, B phase, and C phase. This is for 3 phase. Right? So these are different pads used for the wireless charging. Right. So most of the times we use the circular pads. So in circular pads, sometimes we use this kind of bipolar pads. So that is for to avoid some figure compensation or some mismatches in the elements. Do you have any questions? Do you have any questions? So nowadays, you know that right, battery pack will be something like this. Right. So this thing is known as the battery pack. So in the afternoon section we will discuss about how this battery pack is made or what kind of things are inside this one, right? So this is known as one battery pack, right? This is known as one battery pack, right? So now we have some converters will be there, right? So instead of using a single battery pack, so we can use the multiple battery packs, right? Multiple battery packs. So here the problem is the reliability. For example, something fault occurs in this battery pack, right? So what happens? This is faulty, so we cannot move the vehicle, right? So here if it is faulty, so we cannot move the vehicle. And another thing is that, so to charge this battery pack, if it is a bigger one, right? So you have only one option is there, right? So we have only one option is there. Parallel charging is not possible, at least at one battery pack. So therefore what we can do is that, so we divide this battery pack into several converters, right? So this is what we are using it for bigger electric vehicles or some energy storage systems, right? So here we have one battery pack is there. So multiple battery packs are connected, right? Multiple battery packs are connected. One battery pack, another battery pack. So here also another battery pack. For example, in this case, so 15 battery packs are connected here. Alright? So here the point is that one single battery pack or a bigger one, instead of using a bigger one, so we divided that into 15 parts, and each part is connected to one circuit. Right? Understood? So here what is the advantage here is that the first thing is that fault tolerant. For example, this battery pack is faulty. If this is faulty, what happens is that what we can do is that, so we can bypass this one. Right? So we can bypass this battery. For example, this is faulty, we can bypass this one. Right? So we can bypass this one and we can operate with the remaining battery packs. So that is one advantage. And another advantage is that, so for example here we can simultaneously charge all these 15 battery packs, right? So we can simultaneously charge all these battery packs. So that means it will reduce the charging time drastically, right? If you are charging instead of one battery pack, you can charge the 15 battery packs parallelly. So that same thing we are using in your mobile phone also. For example, if you open some iPhone X or phone, there are two batteries are inside there. Right. In OnePlus phone also they have two batteries are inside there, and when you are charging there, the two batteries will be parallelly charged. Right. So that means here parallel charging means you are charging at double the speed. So that means it will reduce your charging. Theoretically it will reduce the charging by half. So earlier if you took 1 hour, so now it will take only half an hour. Right. So now we can divide it into 15 parts. You can imagine, right? All batteries will be parallelly charged, and it will drastically reduce or cut down the charging time. Right? So this is why it will increase the reliability. So one of the major drawback with the electric vehicle is the reliability. So that reliability and the another one is the reliability and another one is the range anxiety. What is range anxiety? What is range anxiety? So normally you have a fear that you could not find a nearest charging station. So before the battery completely empty, right? So normally if it shows the driving range, right? It will your battery will be empty within 50 kilometers or 100 kilometers. Some people will start anxiety. The point is that you could not find a nearest charging station. That is one thing. And another thing is that the charging station may be busy. You could not find a slot. It's not like a petrol, right? If you petrol, you need to wait for one fuel, right? If it is one vehicle is connected, and you need to wait at least half an hour or 45 minutes, so that the vehicle will complete that, and you complete up, right? Understood? So that is known as charging anxiety, not range anxiety. So one is the reliability, and another one is the range anxiety. So reliability can be increased by using these, incorporating these methods. So whereas range anxiety can be overcome by adding more and more charging stations. Like if you have more charging stations are there in the nearby, so that will increase or that will reduce the range anxiety. Understood? We will stop here. In the afternoon session, we will discuss about the energy storage systems and other aspects. Any questions?
If you have any doubts, please ask. Can doubts in the day?
You can be free and you can ask.
So the afternoon session will be started at 1:30 p.m. So all of you gather here by 1:30 p.m.
In the morning session, we discussed about the battery chargers, right? Different battery chargers, and so next, now we will discuss about what are the different battery configurations are there, and how these batteries are integrated for applications like electric vehicle, renewable energy generation, and microgrid. Okay. First thing is that we require some sustainable energy required. So for sustainable energy, the first thing is that we need to integrate the renewable energy sources into the grid. So do you know what kind of renewable energy sources are there? Can you name any renewable energy sources? So renewable energy sources, can you name any? So solar, PV, next, wind energy, tidal energy, So we have other renewable energy sources as well, like this. So have you ever heard of this? Biomass and biogas. Biomass and biogas. So both are same or different? This one is
Biomass.
this is biomass, right? So here the input for this biomass is the wood, right? So this is the agriculture wastage and some wood fuels is the input for this. So one is the rice husks and the dry fruit outer shells and agriculture wastage and the product that is obtained from the wood processing units. So these are the inputs for this biomass. Right? So we have this one. So these are the fuels that will be input. So we have the furnace will be here. Right. So with this furnace, so we have the boiler. So here it will be the water will be heated up. So from this heating up, right, it will be connected to the dust will be considered. So this is as taken as a thermal power station. So from this steam is generated and steam is passed down to the turbines, right? So from this turbines it is coupled to the generator. So from that it is connected to the transformer and that is ultimately connected to the grid. Right? Understood? So this is biomass. So here the objective is that some wood or something is piled up. So in case of thermal power station, directly coal will be burned. So whereas here the wood will be burned. So all that wood is the wastage of some wood cutting processes. Some wastage will be generated. Some wood bounce and the especially for the rice husks and the dry fruits or some other outer shells of some agricultural products. So that is the input for this. So these things will be generated, means it will be fired up and it will generate the steam. That the steam is passed on to the turbines and turbines will coupled to the generator and that will generate the electricity. Right. This is biomass. Similarly, we have biogas is there. This is slightly different from the biomass. So here the input is the livestock wastage. Right, and some wastage of this one is the input for this one, livestock waste, crops, waste water and the food waste. Right, so we have this chamber will be there, right? So digestive chamber like this, right? So it will generate this biogas, okay? It will generate this biogas. So from this biogas, again we can use it for heating up and that will be used for the electricity. And also this biogas, we can convert this into biomethane. So with this one, so we can use it for the, we can use as a fuel, right? You know this, right? Biomethane. We can generate biomethane. So byproduct of this one is some digestive systems. So digestive, we can use it for the fertilizers, soil environment for the livestock or bedding, right? So this is biogas. So we have other one. This is CHP, it's a combined heat pump, it's a combined heat and the power. So this is CHP is again the byproduct of the thermal power plants. So thermal power plants, some wastage of the heat will be there, right? So from that wastage of heat, so we can use this one. So this one is the boiler here, right? Again here the steam is generated. So from the steam we are generated, so that is gives to the cooling. Understood. So this is some byproduct of thermal power plant. Thermal power plant, it is bigger one, right? Still it generates some speed. So instead of escaping into the atmosphere, so we are reusing them. So power plant will be of the capacity of 500 megawatt of range. So whereas this one will be a smaller one, maybe 510 megawatt of power can be produced from the steam after passing through the main turbine. This is another renewable energy source, that is geothermal power. Right, you know that, right? When you go deep into the earth crust, the temperature will be usually increased, right? So when you go even deeper, so the temperature is very hot. So at that point we will send some water, some kind of thing that is passed on to the turbine, right? So that will be heated up. So that steam will be again brought to the outer layer and again it is passed to the turbine blades. Right? So this especially whenever to extract the petroleum products, we normally have some rig below, right? The rig deep, it will be around 2 kilometers deep or 5 kilometers deep in the earth layer. So from that, whenever that oil is means completely excavated or completely removed, so that will be abandoned. So no one uses it, right? So they normally hide that one. So and from that, so you use this technology to develop some or to produce some electricity. Right? So this is known as geothermal power. So apart from the wind energy, solar, so this is also important. Right? You know that another thing is the wind turbine. So that is a major one. That you know what is how much energy that wind turbine produce typically. How much power one wind turbine will produce nowadays. So here the wind turbine power is massive. Even one wind turbine can produce up to somewhere between 16 to 24 megawatt range. So earlier we have 500 kilowatt range wind turbines are there. So now it is very high. In the morning session, we discussed about the battery chargers, right? Different battery chargers, and so next, now we will discuss about what are the different battery configurations are there, and how these batteries are integrated for applications like electric vehicle, renewable energy generation, and microgrid. First thing is that we require some sustainable energy required. So for sustainable energy, the first thing is that we need to integrate the renewable energy sources into the grid. So do you know what kind of renewable energy sources are there? Can you name any renewable energy sources? So renewable energy sources, can you name any? So solar, PV, next, wind energy, tidal energy, so we have other renewable energy sources as well, like this. So we have heard of this biomass and biogas. Biomass and biogas. So both are same or different? This one is
Biomass.
This is biomass, right? So here the input for this biomass is the wood, right? So this is the agriculture based case, and some wood fuels is the input for this. So one is the rice husks and the dry fruit of the shells and agriculture wastage and the product that is obtained from the wood processing units. So these are the inputs for this biomass. Right? So we have this one. So these are the fuels that will be input. So we have a furnace which we here. Right. So with this furnace, so we have the boiler. So here it will be the water will be heated up. So from this heating up, right, it will be connected to the dust will be considered. So this is as declared as a thermal power station. So from this the steam is generated and steam is passed on to the turbines, right? So from this turbines it is coupled to the generator. So from that it is connected to the transformer and that is ultimately connected to the grid. Right? Understood? So this is biomass. So here the objective is that some wood or something is piled up. So in case of thermal power station, directly coal will be burned. So whereas here the wood will be burned. So all that wood is the wastage of some wood cutting processes. Some wastage will be generated, some wood bulbs, and especially for rice husks and the dry fruits or some other outer shells or some agricultural products. So that is the input for this. So these things will be generated, means it will be fired up and it will generate the steam. That the steam is passed on to the turbines and turbines will coupled to the generator and that will generate the electricity. Right. This is similarly we have biogas is there. This is slightly different from the biomass. So here the input is the livestock wastage. Right, and that's some wastage of this one. This is the input for this one: livestock waste, crops waste, water, and the food waste. Right. So we have this chamber will be there. Right. So digestive chamber like this. Right. So it will generate this biogas. Okay. It will generate this biogas. So from this biogas, again we can use it for heating up, and that will be used for the electricity. Right. And also this biogas, we can convert this into biomethane. So with this one, so we can use it for the, we can use as a fuel, right, you know this, right? Biomethane, you can generate biomethane. So byproduct of this one is some digestive systems. The digestive, we can use it for the fertilizers, soil amendment for the livestock bedding, right? So this is biogas. So we have other one. This is CHP, it's a combined heat pump. So combined heat and power. So this is CHP is again the byproduct of the thermal power plants. So thermal power plants, some wastage of the heat will be there, right? So from the wastage of heat, so we can use this one. So this one is the boiler here, right? Again here the steam is generated. So from the steam we are generated. So that is used for the cooling. Understood. So this is some byproduct of thermal power plant. Thermal power plant, the bit is bigger one, right? Still it generates some speed. So instead of escaping into the atmosphere, so we are reusing them. So power plant will be of the capacity of 500 megawatt of day. So whereas this one will be a smaller one, maybe 510 megawatt of power can be produced from the steam after passing through the main turbine. This is another renewable energy source, that is geothermal power. Right, you know that, right? When you go deep into the earth crust, the temperature will be usually increased, right? So when you go even deeper, so the temperature is very hot. So at that point, we will send some water, some kind of thing that is passed on to the turbine, right? So that will be heated up. So that steam will be again brought to the outer layer and again it is passed to the turbine blades. Right. So this especially whenever to extract the petroleum products, we normally have some liquid with it, right? The deep, it will be around 2 kilometers deep or 5 kilometers deep in the earth layer. So from that, whenever the oil is completely excavated or completely removed, so that will be abandoned. So no one uses that, right? So they normally hide that one. So and from that, so you use this technology to develop some or to produce some electricity. Right? So this is known as geothermal power. So apart from the wind energy, solar, so this is also important. Right? You know that another thing is the wind turbine. So that is a major one. That you know what is how much energy that wind turbine produce typically. How much power one wind turbine will produce nowadays. So So here the wind turbine power is massive. Some even one wind turbine can produce up to somewhere between 16 to 24 megawatt range. So earlier we have 500 kilowatt range wind turbines are there. So now it is very high. You can imagine the size. So that size you can feed at least 2-3 villages. Right? So you can see the size of the wind turbine. So that is 250 meter. Right? The total diameter is 250 meter. So that means the size will be as large as one cricket stadium or even more than that. Right? So you can imagine the size and you can imagine the height here from this. So this height is somewhere around 250 up to 80 meters from the earth outer surface. Right? So those are that much massive when compared to the this. So you can see here, right? So this is 20 megawatt and the diameter is 250 meters. You can imagine the size of that wind turbine. So that single turbine can produce 20 megawatt of power. If you have 5 turbines are there, so that is sufficient to produce one big city. So these are the renewable energy sources. Combining all these renewable energy sources like solar, PV, wind, right? So which is known as the distributed generation, right? So we have conventional generation will be there, so which is based on thermal power plants, hydro power plants, and nuclear power plants. These are the conventional sources of electricity. So whereas those are at same place, right? And bigger one. So this one is distributed generation, or DER, so distributed generation resources. So it is a combination of all renewable energy sources along with the energy storage system, so which is known as the distributed energy resources. Right. So here, so we can integrate the solar power, wind power, geothermal power, and along with that, so we can also increase the battery energy storage system. Right. So there is a combination of renewable energy sources plus battery energy storage system, so which is entirely known as the distributed energy resources. Right. So now it is a popular thing is that, so which is also known as the microgrid. Right. So this is also known as microgrid. You know the main grid, right? You are aware of the main grid, so which is at high voltage. So whether this microgrid is of low voltages, maybe 3.3 kilovolts, 11 kilovolts, or 450 kilovolts, 450 volts. So you see that microgrid. So we have this main grid is there. So from this main grid, so this entire renewable energy sources are connected, right? So this entire all the renewable energy sources are connected to this microgrid. So this will form a microgrid, right? So this is the main grid, and this is formed the microgrid. So we can actually integrate to this one main grid by using some switch or something, right? So we have all we have some storage elements are there, some distribution generation are there, and something like this loads are there, right? So all these wind turbines are there. So all these renewable energy sources, local loads, and energy storage systems, the entire thing will form a microgrid. So this one is microgrid architecture. So this is the medium voltage grid. Then we connected some fuel cells, flywheel, battery, right? And CHP local loads and micro turbine. So all these things are connected to the grid. Right. So this is known as the microgrid. So as we discussed in this morning class, so we have AC microgrid is there and the DC microgrid. So this is DC microgrid. Okay. So we have DC terminals are there. Our system is AC system, right? So here this system is DC. So here the main lines are DC here. So this voltage is usually fixed voltage, right? So this is fixed voltage. So we can integrate the wind turbines here. So wind turbine produce AC power. So from this AC to DC here, right? And another thing is that the solar produce DC. So therefore one DC converter here. And in case of fuel cell, so fuel cell also DC, your DC converter. So energy storage system, this DC converter here. Some PC loads, so we can directly connect. So that means electric vehicle charger, battery charger. So we can directly connect here. So there are some AC loads, computer loads or something like these are AC loads. So this is DC. So therefore what we can do is that DC to AC conversion here. So you get single phase or three phase AC here. Right? And if you want to connect to the main grid, right? So this is DC. So from this DC to AC, so we can connect to the main grid. Right? So here it will operate independently and it is operate with grid connected. Right? So for example, the power flow is bidirectional here. Power flow is bidirectional here. If all these are absent, somehow it will all are absent, right? The power is fed from the main grid to the loads. Right? For example, if the grid is absent, so in that case it is self-sustained. So whatever the energy that is produced in this PV, wind turbine and the energy storage system, right? So that is used to feed the local loads. Right? Sometimes it is excess. So we can also feed this load to the grid and we can get some revenue. Alright? So this is the future. Right? In the future you will not get the conventional like hydro power plant, thermal power plants and all. So here we have some local, we found some local microgrid, one apartment, one something like one office produce some one microgrid. So with that all the PV battery energy storage system will be connected. And it will not rely on the main grid. It is connected to the grid, but it will not rely on that. Right? So that is the future. Maybe in next 4 or 5 years, we are expecting that. So this is in case of AC microgrid. So this one is AC. So earlier it was DC. Right? So AC here. So here we can connect this fuel cells, battery energies, wind turbines, AC generators and all. Right? This is AC microgrid. The difference is where the transmission line is DC microgrid, so here it is AC. That is the reason. That is the simple difference. Right? So we have mixed ones like the hybrid ones. It's a combination of both AC and DC. So this is hybrid one. So one side we have a DC microgrid and the other side we have a AC microgrid. So in between we have some interlinking converters. Right? So in between we have some interlinking converters. So this is DC. So this is AC and this is DC, right? So it can do the job of AC to DC conversion. Right? That's why this is the entire thing. Right? So whenever some surplus amount of power or reduced amount of power is there, right? So from that we can feed the power to the local loads or the main grid. So that is the objective. Right? So as we discussed in future, you don't have a main grid. So only we have the localized grid. So though it is connected to the grid, so we not use. So nowadays some of the industries they will not rely on the main grid. Right? So they will generate their own power. All testing centers or some software industries, data centers, they are not relying on the main grid. So they are equipped with some solar plants, or some wind energy plants, some alternate energy plants, and some energy storage systems. From that, so they are feeding their local loads. If it is excess, they are selling to the or they are sending it to the main grid, and they will get some revenue. If it is efficient, and they will the power is from the main grid to the their loads, and they will pay for that. That's all. Right? So here the point is that so in this renewable energy integration, so one of the major thing that is the energy storage system. Energy storage system is an important thing in the renewable energy system. So one is the renewable energy system is of intermediate nature, right? For example, wind energy, sometimes you know that right, the wind velocity is very high or very low, so we need to stop there. Right, you know that, right? So when it is running very big, there is no much wind is there, right? So it will run at very slow pace and the power generated is very less. So whenever some during cyclone time or sometimes, right? So we cannot run that, right? If it is run at a faster rate, so what happens is that you know that, right? If it is run at a faster rate, so it will completely obstruct the wind. So weight on the actual turbine will increase, so that may lead to the complete collapse of the turbine. So therefore, sometimes it will usually run at velocity somewhere between 50 to 80 kilometers per hour. If it is exceeding that, so they will completely cease the rotation of turbine blades. Right? So they will not leave like that. Right? Similarly, if it is less than that, so in that case also they usually cease the rotation. And in case of PV, so anyway, night time you cannot get any PV, but during daylight, so somewhere it may be cloudy or someday it may be raining, so that impacts very much. Right? So therefore, some form of energy storage is required for the continuous operation. So we have some mechanical one for there. So in mechanical ones, the commonly used is the flywheel. Right? So in case of chemical, so we have hydrogen energy is there, fuel cells are there, these are common. And in case of electrical, so this is AA capacitor, right? And this one is the superconducting magnetic energy storage system. And in case of thermal, so these are sensitive heat exchangers. So these are thermal energy storage. And we have electrochemical. So we have lead acid batteries are there, nickel cadmium batteries, and the lithium batteries are there. So sodium sulfate batteries, redox flow batteries, and hydrogen flow batteries are there. And we have this one, superconducting magnetic energy storage system are there. So anyway, we can't use much of these things, especially mechanical. So flywheel is normally used, but the weight of the flywheel is very high, so that is not encouraged nowadays. And we rely on this hydrogen-based one and the fuel cells. So these are important. So when you have chemical things, right? And we have the electrical. So this is AA capacitors, right? So this one is this is commonly used. And in case of this electrochemical, so we use this some kind of batteries here. Similarly, we also using this superconducting magnetic energy storage system. Right? So mostly we rely on the this one, H2 fuel cells. So this one and this batteries and the superconducting magnetic energy storage system. Right? So now we will discuss about the what kind of batteries are there, and next we will discuss about the supercapacitors. So batteries can become with various chemistries. Right. So commonly used batteries are this lead acid batteries, so lithium ion batteries, sodium sulfur, and the redox flow batteries. So when you are buying or when you are working on batteries, some of the things we need to consider. The first thing is this energy density, right? Energy density in the watt-hour per kg, right? So per kg weight of battery, so how much watt-hour so that will produce. Next one is the cost, obviously, right? So per 1 kilowatt-hour, so how much price it is. And next one is the lifetime. So that is charge and discharge cycles. Charge and discharge cycles. And another one is the power density. Right? So power density kg, how much kg weight, so how much power in watts is generating. So next one is the efficiency. So these are the things we need to consider. The first thing is the power density, energy density, number of cycles that it stands, and next thing is the efficiency and cost. Right. So these things we need to consider. So after that, you can see here lead acid batteries. So what is the disadvantage of lead acid batteries? If we compare lithium ion and lead acids, what you have observed from these graphs? So what is your observation from this? by observing this, so what you understood? So if you talk about the number of cycles, right? So number of cycles means so how many it withstand the charge and the discharge cycles. So if you see that, right? So how many it is? It is very less, right? So hardly 1000 cycles. So whereas here, so it can withstand up to 10,000 cycles, right? So that means the life expectancy of these lithium-ion batteries will be very high. And another thing is that this power density, right? So power density and energy density, so which is also very high here, right? So maybe the cost is somewhat less here. So cost of this lithium lead-acid batteries are somewhat less. Similarly, we compare the other batteries as well. So sodium sulfur batteries, right? Sodium sulfur batteries, what is the disadvantage here? What disadvantage you observe in this sodium sulfur batteries? What disadvantage you observe? Maybe this one, right? So here the power density is very low, right? So whereas the power density is very high here, right? Understood?
Yes, sir.
Similarly, we go for the some redox flow batteries. Okay. So this is the comparison. So we need to make. Okay. So we observe that. So which one is better compared to all? So compared to all, so this lithium-ion batteries are better, right? So compared to all, this lithium-ion batteries are better compared to this lead-acid, sodium sulfur, lead oxide batteries. The energy density is high, number of cycles is also high. So number of cycles high means the life expectancy is high, power density is high, and the energy density is also high. So energy density means it can, what is energy density means? So a lot of energy can be stored. Power density means at one time you can inject huge amount of power, right? So here and efficiency also much better when compared to the other. So that's why so we normally prefer the lithium-ion batteries. Right? So we prefer the lithium-ion batteries when compared to any other batteries. So we have many batteries are there, and the advantages or disadvantages here. So for example, lead-acid batteries, so their energy is poor. Poor weight energy ratios, right? Slow charging, right? And you will require 14 to 16 hours to completely charge this one. So these are the drawbacks of this lead-acid battery. Similarly, this one. So maybe nickel-cadmium batteries. So low specific energy, right? And this cadmium is toxic material and high self-discharge. So this is also one of the important parameters, self-discharge. Okay. So normally when you leave a battery idle, so without connecting any load, right? Sometimes it is expected that it will maintain the charge. Sometimes due to the internal chemistry, so it will discharge on its own, right? So which is known as the self-discharge. So this is one of the important parameters, right? The point is that when the battery is completely empty, right? So when there is 0% charge, if you leave it for a long time, what happens is that the inside chemical material will be there, right? So their properties will be altered, their properties will be changed, right? So that's why we need to avoid the complete discharge of the battery. Right? So they produce some low voltage. These are the drawbacks of these nickel-cadmium batteries. Next one is the lithium metal hydride also. So here, so they can withstand up to 200 to 300 cycles. And another important thing is that the point is that so when to change the battery, right? So when to change your battery. For example, you got an EV vehicle, so you might have understood at some point of time you need to change your battery, right? So you need to identify some point so where you want to change the battery, right? So here, so normally when it is reduced to 80% of the capacity or 80% of the health of the battery, so that is the point you need to change your battery. Let me discuss that in the next slide. So here also at some 200 cycles, 300 cycles onwards, performance will be deteriorated. So lithium-ion batteries, so which is most common one, right? Right. So it is most common one. So we have some advantages like the high energy, low capabilities, right? So long life and high capacity, simple charge algorithms and relatively short circuit times, right? And impossibility to leverage or freezing conditions. So another thing is that, right? So in cold weather conditions, like in some countries in Canada, some part of some Arctic countries, so if you are using some electric vehicles, right? So it will not charge. So normally for to charge the electric vehicle, we require the battery must have some temperature somewhere between the above 0 degree centigrade. So we need to maintain the above 0 degree centigrade. Right? In cold places, if it is temperature is minus 10, battery temperature is minus 10 degrees, it will not charge. So there is additional circuits will be there. So the objective of the circuits will be heat up the battery unit. Right? So it will heat the battery panels so that the battery temperature increase. After that only the actual charge process will be started. Understood? So for all batteries, so you need to maintain certain temperature which is above 0 degrees. So normally batteries will not charge below 0 degrees. In cold weather conditions, so we need to first turn on the heaters for the battery, right? So the battery panels will be heated up. So once it is reached its minimum value, so after that only it will start charging. Understood? And another thing is that in the lithium ion also we have different categories or different classifications are there. So in case of lithium ion, so there are different chemistries are there. So one is LFP, so lithium iron phosphate, and this is NMC, so lithium nickel manganese cobalt, right? And we have this MCA, so lithium nickel aluminum cobalt. So these are the different batteries based on the lithium ion. So by adding some additional materials like the phosphate, nickel, manganese, cobalt, so we slightly modify the performance. Right? So sometimes mostly we use this LFP batteries or this NMC batteries in the electric vehicles. So we use this NMC, lithium, nickel, manganese, cobalt, or this LFP batteries in the electric vehicles. Right? So next thing is their cost. So you can see here, right? Saying around 2030, the cost of this, their cost is in 2 ways. One is the cell, and another one is the pack. We discussed about cell and pack. So you can see here, right? In 2030, their cost is very high. It's almost $650. Right? So whereas now in 2019, so it is reduced to 156. From 2023-24 onwards, its rate is further reduced. It is now it is around $90 or something, right? So as they are extracting this materials from the air, so the cost of once it is in mass production, so their cost is drastically reducing, right? Next we will discuss about so how batteries are these battery packs are generally fabricated for the electric vehicles or the energy storage systems. Right. So here we normally think that so battery pack consists of one bigger battery. So that is not the case. So it consists of some small batteries of some small size AA size. The batteries are just slightly above AA size batteries will be there. Right. So this is one battery pack. So it consists of multiple batteries, right? It consists of multiple batteries, so which are usually connected in series parallel, right? So these are connected in series parallel. You know that, right? Series connection will increase the voltage, and parallel connection will provide the multiple current paths so that we can increase the current rating. So series connection increase the voltage rating, parallel connection increase the current rating. So this is one cell, right? So this is cap here, and we are supply here, so anode cathode, and we are everywhere. So this is one battery, right? So this made of several batteries, and here this is the electric vehicle. So normally, so this battery pack is placed just in the floor pin, right? So just where the place where they are seated, right? So just below that, so we place the battery pack, right? So why we are placing that one? Because the weight is very high, right? The battery pack usually weight is very high. If it is taking somewhere between above a place, right? So what happens is that if it is above, what happens? The center of gravity will be, it will change, right? If the weight is increased into the middle, right? So it will increase the center of gravity. So in that case, when you are cornering or when you are driving at the corner, so the centrifugal forces acts, and that leads to the rollover of the vehicle, right? So therefore, we will keep the vehicle as low as possible. So that's why you know that the sports cars, they are not very tall. The sports car or some performance cars, their height will be very less, right? So they are as close as to the earth point, right? As close as to the earth surface. So therefore, the center of gravity or the centrifugal forces will not act on that, it will not lead to the rollovers, right? So usually mounted on the floor pin, right? So this is the point where the outboard charges will be placed, and these are the battery packs. You see here, right? So multiple battery packs are connected here. So each battery pack consists of several individual batteries. So now the point is that, as we discussed, each battery pack is having some voltage. Right? As we discussed, we have 400 volts batteries are there, battery packs are there, and 800 volt battery packs are there. Right? So now the point is that, so when we use 400 and when we use 800 volt batteries. Right? So here, every days or nowadays, what happens is that we are moving with the 800 volts battery packs. Right? So let us assume that we have the motor capacity of some electric vehicle motor capacities. So let us assume it is 200 kilowatt motor. Right? So assume that it is a 200 kilowatt motor, and the that the efficiency is in 100%. So AC power is equal to the DC power. So AC power is equal to DC power. So here imagine we have a 200 kilowatt motor is there, and that is also equal to the DC power, and the voltage is 400 volts. So how much current it will draw? If the power is 200 kilowatt and the voltage is 400 volts, how much current it will draw? Hmm? 200 kilowatt by 400, how much it is? 200 kilowatt divided by 400, how much? 500 ampere? Correct? How much it is? 550? I am asking a simple question. Okay.
0.5.
200 kilowatt divided by 400. How much it is? 500 or 50?
50.
50, right? Correct? 200 kilowatt, so that means 2 lakhs divided by 400, how much? How much it is? 500 amperes, right? Correct? So that means each device or we know that like converters are made with some switches like IGBTs, MOSFET, right? So each device is supposed to carry that much of amount of current, right? So huge amount of current that is carried by each switch. So normally that kind of switches are not available. What they normally do is that they will connect multiple switches in parallel, right? So in a converter, we represent only one switch, but in actual case, there are multiple switches are connected in parallel. Right? For example, 500 amperes we need to package, so that switch is not available. Only 100 ampere switches are available. We need to connect 5 switches in parallel. Right? So the drawback with the parallel operation is that we expect that all supposed to carry the equal current. Right? So all is expected to carry the equal current, and all are expected to on at a time. So one device is on early, right? So that means all the current will flow through that device only. So 5 devices are operating parallelly, one device is turned on early, so that means all that 500 ampere current will flow through that device only. So that device will be damaged because its rating is 100 amperes and you are passing 500 amperes, the device will be damaged, right? So the parallel operation is very difficult. Okay. So the point is that we are representing a single switch or single MOSFET or IGBT, but actual fact is that is combination of or connection of several parallel connected MOSFETs or IGBTs, and the entire represent one switch. And we expect that the switch will be turned on and turned off, all switches will be turned on and turned off simultaneously. If one switch will turn on early, all the current will flow and the device will be damaged. Right? So therefore we need to take some extra protection like equalizing circuits or something we need to do. So if we are choosing 800 volt architecture, what happens if you choose 800, right? The current will be reduced by half, right? So now 200 kilowatt divided by 800. So previous compared to that, the current is reduced to half, right? So now no need to go for 5 or 6 switches in parallel. Maybe 2-3 switches are sufficient, right? So compared to operating 4 switches in parallel, so we can easily operate 2 switches in parallel, right? So that is the advantage. So you have, and another thing is that basic things, right? So when you are increasing the voltage means you are reducing the current, and I square R losses will be reduced. So that's why most of the manufacturer automobiles they are moving for the 800 volt architecture to reduce the current. So when the current is reduced, number of parallel connected MOSFETs or IGBTs are reduced, and that also reduces the I square R losses. Right? So now the point is that if we require to generate 400 volts, so if you want to generate 400 volts from that, so as we discussed, we need to connect several batteries in series. Right? So here each cell will produce only 4.2 volts. The cell we have shown, right? This single cell will produce only 4.2 volts. Correct? So that means we need to connect 400 switch. We need to obtain 400 voltage. So how many switches we need to connect means? So we need to connect 96 switches in series. So we need to connect 96 small batteries in series so that we can get 400 volts. If we require 800 volts, so we need to connect 192 cells in parallel. Understood? So each single cell producing just 4.2 volts, but the battery pack is 400 volts or 800 volts. So what we do is that, so we need to connect 96 switches or 96 batteries in series to produce 400 volts, or if you require 800 volts, you need to connect 192 cells in parallel, in series. Understood? So how it is connected means, so one is like this, and the other one is usually connected in the opposite direction, so that it will form a series connection. One battery is like this, the other battery is connected in the opposite direction, so that one common tape will be run across all. Understood? So that will form a 400 volts battery pack. Right? So if you want to increase the current rating, so what you are supposed to do? So we need to connect this this kind of 96 cells in parallel, right? So we have one row of 96, one column of 96 cells, so another column of 96 cells, another column of 96 cells. So that will increase the current rating, right? So therefore, so if you want to increase the current rating, so here, so this is one battery pack, right? So another one will be connected parallel, right? And two battery packs are currently parallel. Understood? So one small cell produces small voltage, right? So just 4.2, right? To make it 400 volts, so we need to connect so 96 such cells in series, right? Similarly, we have this ATP, right? So meaning is that so we have 80 parallel bonds are there, right? Such cells so which are connected 80. So that means how many cells are there in one battery pack? So how many cells are there in battery pack? So this 96 into multiplied by 80. So that many batteries are there inside. Understood? Understood? In one battery pack, so 96 cells which are connected in series, such series paths are there, 80 such series paths are there. Right? So that means, so this is 96, so this is another 96, another 96 and so on, so up to 80. Right? So that will form one battery pack. So that means, so here, in one battery pack, so this one side batteries will be 96 into 80 will be there. Understood? So that's why it is known as 96S, S means series, and 80P, 80 parallel. Understood? So that thing will form a one battery pack. Understood? Okay? Such several battery packs, so which are used. So you can see here, so this is one battery pack, right? 96S, 80P. So this is another battery pack, another like this. Alright? Understood? So now we know that, right? Some manufacturers, for example, are buying some EV, they usually ask what battery pack capacity you want, right? Some vehicles may be 60 kilowatt hour, or some may be 75 kilowatt hour, or 90 kilowatt hour, right? So usually, if it is each one usually produce 15 kilowatt hour, so typically each one will produce 15 kilowatt hour, right? So for example, some requires 60 kilowatt hour, so they will give these 4 battery packs, right? Someone wants more, 90 kilowatt hour, so they will give it these 6 battery packs. Understood? Okay? So this is how they will give the different sizes of batteries, different capacities of batteries. Right? Earlier, so this is used for the energy storage system. The same concept we are using for the electric batteries also. The same way, so we also use it for the energy storage system, but the voltage and the current ratings are slightly different. Right. So now we need to protect this battery, or we need to increase the life expectancy of this battery. So for that, so you need this BMS. So what is BMS?
Battery management system.
So BMS is the battery management system, right? So its objective is to
manage the
maintain the health, safety, and life expectancy of the
battery.
So that is its objective, right? It also maintains the charging algorithm, how it is charged, temperature increases, protection. So everything is incorporated here. So it is both software and hardware approach. So physical hardware will be there, and also some software are also inside it. This is just like a computer, right? It is just like a computer. Everything is integrated to this. It's a machine kind of thing. Right? The first thing is that, right? So whenever there's some non-uniformity of charge, for example, you expect that expect that so all the battery packs are simultaneously charged and discharged equally, right? Not like one is charging at one rate and other is charging at other rate, right? So we expect, for example, 9 are connected, 6 are connected, right? So we normally expect that so all the battery packs are simultaneously charged or discharged. In other words, so if we expect that all must be equally distributed power, right? So motor requires some power, so that power is supposed to be equally distributed by these units, right? So that is one thing. Like another thing is that the charge counter mechanism. It is expected that so we need to maintain the health of these battery banks, right? So the main objective of this battery BMS is divided into three things. So one is the performance optimization. So one is the performance optimization. So next one is the safety. Another one is the multi-cell management. Right. So there are three things are there. So one is the performance optimization, safety, and this is multi-cell management. Right. So here you know that, right? So nowadays some of the electric vehicles, especially two-wheelers, are catching fire. So one of the main reasons for this one is the improper design of BMS. Right? If something is faulty or something is there, so it will immediately, BMS will immediately detect that and appropriate action will be taken. Right? Otherwise, if it is leave like that, so at some point of time it will catch us the fire. Right? Or it will completely destroy the battery. So therefore, a proper design of the BMS is essential for the maintenance of the battery. First is look at this performance optimization, right? So we have some requirement here. So one is the charge and discharge cycle optimization, charge and discharge cycle optimization, state of charge. So what is state of charge? What is state of charge? We know that whenever someone asks how much battery percentage you have, we answer 70%, 80% like that, right? The technical word for that one is the state of charge, right? The technical word for that, so how much battery is there, 80% or 90%, so that is state of charge, right? So we cannot ask like that, what is the state of charge of battery, right? So your answer is how much battery we have, right? And another one is the state of health, right? So we there are certain things which are associated with the health of the battery. So one is the SOC, right? So SOC, so that is state of charge, say releasable, that is charge releasable by charge rated, right? Charge releasable by charge rated, so in percentage, alright? So next one is the state of health. So this is one of the important parameter. State of health, so which is one of the important parameter here. So meaning is that, for example, you purchase one battery, right? So they have mentioned in the name that they have given that 60 kilowatt hour battery or something like that, right? 60 kilowatt hour battery, so that you purchase, right? So after using it for several years or several days, what happens? The capacity will be reduced, right? Its capacity will be reduced. Maybe after you purchase 100 kilowatt battery, and maybe after 3 years its capacity is actual capacity reaches to 90 kilowatt hours, right? So this is state of health. So this is C rated. So when you are purchasing that, so that comes with some rating, right?
Yes.
So 10 kilowatt, 100 kilowatt hour. So this is C maximum. So this is C maximum. So after 5 years the capacity will be reduced, alright? So this is 100%. So this is the important parameter. So when to discard your battery, right? So this is the point. So when to discard your battery for optimum performance. So whenever you have detected the state of health, which is 80%, right? So which is 80%. So that is the point where we need to change the battery. right?
Yes, sir.
So that means you purchase some electric vehicle with 100 kilowatt hour, right? After 7 or 8 years, you observe that the actual capacity is reduced to 80. So that means 80% when it is reached state of health. So that is the point where you need to discard and you need to buy a new battery. So if you continuously run with some reduced capacity, the first thing is that it will take more current, right? Whatever the benefits you are getting from the EV, right, that will not get, that is, if you to charge that, so you require more current, and another that it will also increase the temperature and it will also increase the, or it will also not, that means the charging is not efficient, right? Understood? So state of charge is, so what is the rating of the thing and how much it is releasable. So how much of amount of charge it can release. So if it is 100%, so charge is 70% is still there, so that is 70% is your SOC. Similarly, state of health, so when you are buying on the nameplate value by present value divided by nameplate rating, right? So depth of the discharge, right? So depth of discharge, so this is C released by C rated, right? So that means already over. DOD means, for example, here 70% charge is there, so that means the 30% is already discharged. So this is DOD, depth of discharge. So that means theoretically, so DOD equal to 100%, right? So SOC equal to 100% minus depth of discharge. Understood?
Yes, sir.
So and another important thing is that, so there is no tool or there is no sensor or nothing is there to actually measure the state of charge, right? So all are estimation techniques only. The point is that no, if it is current, we can measure from unmeasured voltmeter, right? So for measuring the charge, how much percentage charge is there? So there is no device is there, right? So no sensor, no device, or no equipment is there. So all the things we need to estimate, right? So how much percent is there or how much it can be spent? So we need to estimate. Right. For example, you can in your phone, for example, show it 70% of battery, and it will show, right? So how much time still you can run the phone, right? So those are all estimations only. There is no proper sensor or nothing is there, right? So if you observe that when your phone becomes old, still it is showing 70%, 80% charge, then within half an hour, it will completely empty, right? So that thing you might have observed, right? So that's why, so there is no sensor or no measuring equipment for the estimate of measuring this SOC. So we need to estimate it, right? So we need to estimate it. The different methods are there. Some commonly used methods are the Coulomb count method. So this is Coulomb count method. So the SOC presently, so previous value by 1 is generated. So what is the current that is flowing out, right? So what is the current that is flowing out from the battery, and this is the loss component. So every tau seconds, so we need to integrate that. So how much current is going, so based on that, so we can estimate the battery SOC. Understood? So one method, Coulomb counting methods are there, some other. And another thing is that, so some open circuit methods are there. Like we normally think that when the battery is completely discharged, right? So how much voltage is there? Most people think that the voltage is 0. So that is not the case. So when the battery is completely empty, so the voltage is not 0, right? So you can see here, right? You can see here. So this one is the open circuit voltage of battery. So if it is very less charge is there, the voltage is just 340 or something, right? So when the battery is fully charged, right? So voltage is around 400 volts, right? So that's why it is given in the instructions. Even the battery is completely empty, you should not touch the terminals with bare hands, right? So you must use some protection before touch these terminals. Understood? So many things that the battery is completely empty means it is not 0 voltage. Some voltage will be present. Correct? Understood? So based on this open circuit voltage, for example, some voltage is detected somewhere, right? So accordingly, so we can estimate the how much charge is there. So like that we can estimate. Understood? So we have methods are there just to estimate the state of charge. So there is no direct measurement for this, right? So there are some methods of Coulomb counting methods. So how much current is flowing every some sample time, maybe one second or 2 seconds. So they will integrate that. So from that we subtract that. So we will get the state of charge. So another method is the open circuit method. Like in this, so we have something like that. So every time we measure the voltage, so we have this graph will be there. So that is provided by the manufacturer. So based on that, so the open circuit voltage we will measure. So maybe we can not accurately here. So maybe you can estimate that this much battery is left. Correct? So there are some other advanced methods are there, like some neural network based methods, so which is common nowadays. Right. So we have all the information like terminal voltage, discharge current, and temperature of the batteries. Right. So you might study right. This one is based on the back propagation neural network. So that gives you the state of charge. So all these AI techniques, machine learning algorithms, so these are used for the estimation of this battery charge. Right. So here, whenever some estimation or whenever some thing is there, right? So best choice is to use the machine learning or the artificial intelligence methods. Right? So if your direct measurement is there, like if you know the how much voltage or current or something is there, so no need to go for the methods. So we can directly measure it. Right? Understood? Other methods also there, right? Like this is estimation of battery when the battery is fully charged or not. So this method that is advanced Coulomb counting or the improved Coulomb counting method. So this is also used to estimate the batteries. We are here, right? As we discussed, the BMS is an important thing is that, so one is performance optimization. So the main requirement is the charge cycles, optimization, state of charge and state of health. So adapting the performance with temperature, right? So adapting the performance temperature. When the temperature is increasing, so it will cut down the power. If it is exceed the limits, it will completely shut down, right? So optional thing is that internal resistance and state of life estimation. So these are the main requirements of this first one. So BMS actions is that what exactly it requires. So you must know the pack voltage, pack current measurement. So you must know the ambient temperature, right? So ambient temperature here. And for estimating the SOC, you may require some methods like Coulomb counting method. So analyze the performance, state of health methods. So all the data will be there. So different charging cycle, every time charge cycle is there, right? So we have the, so every time it is charging, right? The data will be stored. So this is how the machine learning objectives will come. So whenever you are charging, every time all the data will be monitored in the system. So how it is charging, how it is discharging, so everything is monitored, right? So the state analyze performance, state of health. So nowadays in the cars also it will show. So what is the health and what is how much amount of current is flowing, what is the voltage of the battery. So every information is displayed to the user. So implement the battery model and analysis. Right? So we can implement the battery model and analysis. So what are the objective is that so we are doing so, right? So we can optimize the battery pack life. So that means we can increase the battery pack life and we can optimize the energy store. So that means we can maximize the energy store and we can utilize the maximum amount of stored energy, right? we can utilize the maximum of the stored energy and maximize the mileage range. Right? We can maximize the mileage range. And another thing is that, for example, if it will not wait until the battery completely discharged. Maybe some small percentage of battery will be left. Right? Some small percentage of the battery will be left. So before that only it will be completely shut down. So next thing is the safety. Right? This is another important thing is that. So requirements here. The first thing is the safe and the rapid charging. Right? So here the charging must be safe and also it should be quick. Right? Charging must be safe and also it should be quick. Alright? So you know that, right? Early days, for example, when we are using mobile phones in somewhere between 15 years ago or 20 years ago, battery capacity is very small. And it will typically take at least 3 hours to fully charge the battery. The capacity is very small, just 1500 milliampere hour, but it will take a lot of time to charge. Very quickly. You know that, right? When early days, when we are using some mobiles, the battery capacity is very small, so 1500 milliampere hour only. It is usually take 2 hours time, 2 hours, 3 hours time. So nowadays, how much time it is required to fully charge the battery? How much time is required?
3 hours.
3
hours.
How much time is required? 20 or 20 minutes, 1 hour, 45 minutes, right? Depending on the what kind of mobile you are using. If it is a Oppo or Realme, right? So we have 100 watt chargers are there, 150 watt chargers are even 250 watt chargers are there, right? If you connect some 250 watt charger, it will already take 7 minutes to fully charge the battery. Just 7 minutes, right? And the point is that even you are injecting lot of amount of power into that, still the battery can be used for several times. So without we can use it for 4 or 5 years, right? So without much damaging to the battery, right? So that much technology nowadays is developed, and also switches, right? So the switches are operated extremely fast. In case of this inside the battery, we have switches will be there, right? So they are operated very fast. So normally, for example, you are using some MOSFETs or something, right? They are operated at the 2 megahertz range. So that means in 1 second, inside your mobile, that will turn on and turn off by 2 million times. Right? You can imagine that how fast it is. Okay? So that's why the batteries are compact and they are very fast and the power density is very high. Right? And also it is much safer than the earlier generations. Right? So here what we need is the safe and rapid charging. The charging system must be safe and also we need to be fast. And over voltage protection, so as we discussed, the battery consists of some voltage limits. Right? So these are the limits of the batteries. Right? For example, this is the lower limit and this is the upper limit. So it should be operated within the limits only. Right? So when you are charging the battery, it's supposed to maintain, for example, in this case maybe 330 volts, somewhere around 400 volts. You have to apply this voltage only. You should not apply less voltage or you should not apply more voltage. If it is over voltage, it must be protected. Right? The battery must be protected from both power voltages and the under voltages. Right? So over discharge protection, right? Over discharge protection, so meaning is that so it is completely discharged, right? So it's supposed to turn off. In your mobile also, when it's completely discharged, it is turning off, right? But the fact is that still some charge is there, right? It is not completely 100%. Even if it is completely off for us, from the battery point of view, it is not completely discharged. So small amount of charge will be there, right? So that is for protection of over discharge. If you keep it left switched off, so for few days, like 1 month, 2 months, right? So that's supposed, the cell chemistry is supposed to maintain, right? So for that, So they will keep some charge. Alright? So they will keep some charge inside the battery. Alright? So that's why you need some over discharge protection. And another thing is that so discharge current is also we need to consider. If the battery rating is 20 amperes, we have to keep sure that supposed to maintain 20 amperes rating only. So that means over discharge in both ways we need to maintain, and over temperature protection. If the temperature is also exceeding the limit, right? So temperature exceeding the operating limit, so we need to protect the battery. So heat management and the cooling system. So normally all the batteries are liquid cooled. So all the batteries are liquid cooled. So meaning is there some liquid. So inside this battery pack, some small liquid will be circulated, right? So non-conductive liquid will be circulated, and we have similar to the transformer. So we know transformer too, right? Some small liquid is connected, right? So it will be circulated through outer layer, and it will completely circulate in the transformer, right? In the same way, some small cooling, some force cooling is circulated inside this battery pack. So next thing is that so thermal runaway. What is thermal runaway? So thermal runaway is the cascade of the increase in the temperature. So normally when the temperature increases, you know that the positive temperature coefficient and the negative temperature coefficient. So when the temperature increases, in some cases the resistance will reduce, right? So here also when the temperature increases, it will draw more and more current, and if it is drawing more and more current means the temperature further increases, right? So therefore, so at some point of time temperature will drastically increase, so we need to avoid that. So this is known as thermal runaway. So this is cascade increase of the temperature. So low temperature charging management. So low temperature charging management. So as we discussed in previous just now, so in cold countries we need to maintain the cell temperature at some certain value, right? Further, you need to heat up the charger, right? You need to heat up the battery pack. So with this low voltage, low temperature charging management is further, right? So these many things we need to incorporate. So further, again we need to measure the cell voltage and peak current measurement. This peak current measurement is for the this one over discharge protection, thermal runaway, heat management. So this peak current measurement is required. Cell temperature measurement. Alright. And correctly distribute the capacity to all. Correctly distribute the capacity to all cells within the pack. Right. So here the power is supposed to distribute equally. We have multiple single batteries or small batteries will be there. So the power is supposed to distribute equally to all. And fusing of individual cells. So each individual cell is connected to some fuses. Some if it is excess or something like. So in that case the fuse will be blown out. So if you are doing so, you get these things. So correctly utilize the available battery capacity and maintain the cell voltages within the limits, and maintain the cell temperature within the limits, and ensure extremely minimal risk of fire. And we can ensure that an extremely minimal risk of fire. Understood? So next one is the multi-cell management. The next one is multi-cell management. So here, this is another important thing, right? So if there are multiple cells are there or multiple battery packs are there, so we have to make sure that all the battery packs are simultaneously charged or discharged, and at the same time the power distributed by all the battery packs are supposed to be same, right? The power distributed by all battery packs are supposed to be same, right? So let us consider there is some small case, right? So let us assume that this battery pack is excess charge, right? So this battery pack is excess charge when compared to the others, right? So the objective is to maintain the charge equal, right? Let us assume this is 70%, this is 70% charge, and it is 80% charge in there, right? So under this case, there are two options are there. So one is the active self balancing and the passive self balancing. Active self balancing and the passive self balancing. In case of passive self balancing, so whatever the excess charge is there, right? So we normally connect some small resistances, and that excess charge is dissipated through the resistances. Understood? The excess charge is dissipated through the resistances. Obviously, lot of wastage will be there, right? So this kind of methods are not encouraged. So we have passive self balancing. Meaning is that this is having excess charge, right? So between these, so we have DC-DC converters are there. So between these battery packs, so we have DC-DC converters are there. So when it is excess charge, right? So this excess charge is transferred to the remaining battery packs, right? So this excess charge is transferred to the remaining battery packs. That is internal adjustments. If you have excess thing, right? So that for example, it is 80% is there, 70%, right? So it is 80%, whatever this battery, right? So it will continuously charge these two batteries until all their powers are, all their responses are equal. Understood? So this is known as active self balancing. Internally we have some DC-DC converters, so that converters will do the job. Right? So the objective is that every time, so we need to maintain the battery state of charge equal. Right? Every time the state of charge is equal for the optimum performance or equal thermal performance. Right? So one is having higher voltages. For example, this is having highest charge. Right? For example, this is 50% charge when this is 80% charge. Right? So what are the complications we have? If it is 80%, this is 80%, this is 50%. Right? So here the point is that 80% we have one charging algorithm. Right? Similarly for 50% we have one different charging algorithm. Right? So we cannot use multiple charging algorithms, right? So that's why, so we make everything into same SOC. We bring everything into same SOC level so that we have one charging algorithm. Alright? Understood? So depending on the SOC percentage, your charging algorithm changes. As we discussed, if it is 90%, it's 0 to 80%, the charging will run at a faster rate. When it is touching 80%, 82%, it is one rate. From 85 to 90%, it will operate another rate of charging. Likewise, from 95 to 100%, usually it will take more time, right? That means, for example, this is 95%, 95% charge is there, this is just only 30%. We cannot have the same algorithm, right? So that's why when it is 95%, so this charge is transferred to the other battery packs, right? So that's why another thing is suggested that, so when you are replacing battery pack, you should not replace individual pack, right? So that means, that's why this common thing is written on the batteries, right? We cannot mix the old and the new batteries, right? Same applies here, we cannot mix the old batteries with the new batteries, right? So their performance and all things will be different. And also we have to make sure that all the batteries of the same rating, same capacity and same manufacturer, and they are manufactured at the same time for the optimal performance. Understood? Right? So that is known as the multi-cell management. The meaning is that if you have multiple battery packs are there, so our objective is to equally distribute the SOCs, and at the same time we have to make sure that all the batteries are, for example here also, whenever it is connected to the motor, right, so you have to make sure that all the battery packs are delivering equal amount of power, right? They are delivering equal amount of power in both charging and discharging modes. So then only automatically their SOC and their performance will be equal. So here, the multi-cell management, so many parallel connected, so blocks of cells are connected in series strings and pistons, so distribute charge uniformly across all the cells. So manufacture mismatch of the cells, for example, some manufacturing mismatches are there, so that also you need to take it care. So pre-gradation of cell capacity, so degradation of the cell performance over the lifetime. So for that we need is that cell voltage measurement over current and non-current alarms, cell temperature measurement over current and non-current alarms, and cell balancing as we discussed, active and the passive. So passive is just we will dump the excess charge in some resistor or somewhere, right? So whereas active is transferred to the other battery unit, right? So by doing so, we can increase the battery pack capacity, we can optimize the energy storage, and we can utilize the maximum amount of the stored energy. Understood? So these are the three main objectives of BMS. So one is the performance optimization, safety, and another thing is the multi-cell management. As we discussed, so BMS is just not a software, it's a combination of both software, hardware, and some machine learning algorithm or something. Right? So this is how the BMS is there. As we discussed, so BMS is supposed to perform this task. So battery pack voltage and current measurement, right? So we need to determine the cutoff points, right? So we need to determine the cutoff points at what point of the current and what point of voltage we need to cut off the power supply, and we need to battery ambient temperature measurement and control. So here the ambient temperature means the surrounding temperature, right? But the point is that normally we have ambient temperature is usually room temperature, which is around 24 degrees or so, right? But the actual practice is that all these things, all the converters everywhere in place with some, that is also dissipate some heat, right? So all these converters also heated up, so the ambient temperature is usually much higher than what we have. Normally the ambient temperature is around 40 degrees or 50 degrees centigrade, right? So that means the battery is already, the minimum temperature of the battery is around 40 or 50 degrees centigrade. Right? The cell voltage measurement, so we ensure correctly, so distribute charging, so cell balancing, duration charging, so we equalize the charge on the individual cells, so cell temperature measurement for the selected cells, so protect against the heating and the charging. Right? So impedance measurements, and also we need to, as we discussed, so these are model-based calculations, right? So these are model-based calculations, no direct measurements, state of charge, state of life, health, and state of life, and available and the remaining mileage, or in other words, the range of the vehicle with the remaining charge. These are the some power components that are used in the BMS. Some microcontrollers, graphical interface is also used to display to the user. So next we move to the other one, right? Supercapacitors, right? Supercapacitors. So batteries and supercapacitors are similar thing, but they are slightly different. So battery having higher energy density. So whereas superconductors have the highest power density. Right. So these are the commonly used ones, and they things. So one is the battery, supercapacitor, plug-in and fuel cell. Right. So these are the most commonly used ones. So one is the battery, supercapacitor, plug-in and the fuel cells. So we have a lot of factors are there based on 10 scale. So one is the cyclability, so that is repeatedly charging and discharging, cell voltage, charge retention, alright, and temperature range, power density, energy density, affordability, that is cost, and affordability based on the energy, and affordability based on the power, right? affordability based on the power and affordability based on the energy. Right? So if you observe that the super capacitor is the blue one and the battery is the red one. Right? So you can compare this blue one and the red one. Right? So you can see that the affordability for the super capacitor is high. Right? So this is in affordability for the energy will be high, and also you can see the power density. So power density of the super capacitor is high, and whereas the energy density, so this energy density of the battery will be high here. Correct? So this is the comparison between the performance comparison between the battery super capacitors. So the main thing is that the super capacitor is highly recyclable, alright, and the power density is very high. So that means we can charge the super capacitor very quick, right? So we can charge the super capacitor very quick. The only drawback is that it cannot store more energy. Like battery can store more energy, right? So battery can store more energy, whereas super capacitor cannot store more energy, but it will pump more power to the system. That means it will absorb more power and at the same time it will give more power. Right? So this super capacitor used in the transport systems, right? That means you can inject more amount of the power into the super capacitor. Battery takes less amount of power, whereas super capacitor you can increase the sudden charge into the super capacitor. Right. So that's why in the especially in the metro buses in some foreign countries, so they have the charging stations at every stop. Right. The stop is usually for 15 to 20 seconds or at most 30 seconds. Right. So during that 30 seconds period, the vehicle will be charged. So inside that we have some super capacitors. The super capacitor will quickly charge that within that 30 seconds. Right. So how long it will run? So until the next stop, or maybe maximum 1 or 2 stops. Alright. In the next stops, again it will charge, and again it will run continuously. Right. So that means it will add some extra boost thing. Right. It will add some boost to the existing charge. Right. Understood? So super capacitors are used for this one. And another thing is that we need to plug the both super capacitor and the batteries. Right. So for example, in case of regeneration, so we need to quickly absorb the power. So for that, first we transfer to the super capacitor. From the super capacitor, we can slowly transfer to the batteries if required. Understood? So super capacitor will quickly take the energy and quickly give the energy compared to the batteries. But the disadvantage is that they size or their energy density is very small or much smaller compared to the battery. Right? So that means we require a larger system or more number of super capacitors to form a equivalent amount of power that's stored in the battery. And another thing is that in super capacitors the voltage rating is very less. Batteries, the good thing is that we can increase the voltage levels by changing the chemistry, but the super capacitor we cannot do that. The maximum voltage of super capacitor is somewhere between 2.6 to 2.9 volts only. Super capacitor voltage is 2.6 to 2.9. Similarly, so we need to connect several super capacitors in series to produce the required to get the required amount of voltage. Right. So, but whereas batteries, by changing the internal chemistry, we can change 12 volts, 48 volts direct batteries are, so we can make it. Right. But super capacitor is not possible with a single cell. A single cell, the maximum voltage or the range of voltage between 2.6 to 2.9 volts. This is super capacitor principles. So this is also known as the double layer capacitor. So normal capacitor and the double layer capacitor. Right. So there is an extra layer here. So this is diffuse layer and the contour layer. In case of capacitor, we have only this diffuse layer will be there. But in case of super capacitor, we have both diffuse and the same voltages. Both layers will be there. Right. So these details are not very much important. this is an equivalent circuit of supercapacitor, right? So we can model the supercapacitor like this, some resistance, and this from the series resistance in parallel with this, and also some capacitance. So this is the supercapacitor capacitance, and this is the loss model, parallel loss model and the series loss model, right? So this is the series capacitor, this is supercapacitance, right? Some loss model. These are all the different models of the supercapacitor. So this is the actual capacitor. So this is the actual capacitor, and rest of the things are the loss models. We have different losses at different stages, some losses at the different layers like that. So battery management system, BMS is for the batteries. Similarly, we have this SMS. So this is supercapacitor management system for the this one, right? Supercapacitor management system here. Same thing here also, right? So SMS, the main functionality is protection here. So same over voltage protection, so reverse voltage, over current, short circuit protection, over temperature protection. Similarly, performance management, voltage, current, temperature monitoring, state of charge, power lines limit, estimation of parameters, cell balancing. So upon flag, this is all these things. So POC, communication, data recording, reporting, right? So pre-charge contactor protection. So these are all the inherently built in the SMS, that is superconducting. So supercapacitor management system. Understood? So this is also similar to the BMS. So this is based on the both software and the hardware architectures. Right. So we have a pre-charge contactor will be there, and we have super pack will be there, and all these things are connected to the some processing unit. So that is electronic control unit, is known as ECU. So we have protection, state of charge, state of health, state of power, and we have fault diagnosis and the thermal management. So all will be included. Right?
Good afternoon, sir.
Yes.
Sir, battery యూజ్ చేసిన తర్వాత సెల్ని పడేస్తాం కదా, అలా పడేస్తే అది హజార్డ్ అవుతుంది.
Yeah, we need to properly dispose that, right? See here, all these batteries contain some toxic materials like some cobalt. So in general, as we discussed, for this lithium-ion batteries doesn't contains a huge amount of or the maximum amount of hazard materials, but some other battery like cobalt are very dangerous, right? So we need to properly dispose that. Right? So here the World Health Organization and the UNESCO or some other they're focusing on that. So they're developing the so here every manufacturer, so they have to buy the batteries, right? And they must have the proper unit for the complete recycling of these parts, right? So they cannot throw like that. So whatever the wastage of this will be, usually non-recycled wastage will be dumped into some islands. So where some secluded islands will be there, right? So that material is dumped there. So where it is reusable, so that will be again reused, right? So when you are starting with some battery variant, so you must have a battery disposal units as well, right? So you must handle that. You need to buy back from the customers. So from the customers, you need to properly disintegrate that. So whatever the hazardous materials will be there, so that should be properly done. Right? That is the thing you need to follow.
Anyone?
Aman, nuala rawabu.